Hello, Amiga Fire. Hello, Jamaica. Hello, Doodle Trap. Hello, average person. I'm glad I got the average person in here. That's neat. Okay. I mentioned this last time when we did the math course that I'm going to try to have this be a very practical and visual approach to what we're doing in order to get into shaders. As before, feel free to ask questions at any moment. I will be primarily reading the chat, the Future Games private chat. One of the questions people have quite a lot is like, what is a shader? And some people ask the question of like, do I need shaders in my project or should I use shaders? And the easy answer to that is that you kind of don't have a choice. Everything in a game is rendered with shaders. There are some exceptions, but these days, pretty much every game you play are like rendered with shaders absolutely everywhere. So what is a shader? You can think of a shader as code running on your GPU. That is kind of the most generalized way that I can think of defining shaders. But in this case, we're going to focus on shaders that specifically render graphics onto your screen. And quite often what you do is that you define a bunch of parameters, like maybe the position of an object. You have data such as a mesh you want to render. Maybe you want to render a cat in a game. Then you have a mesh of that cat, and then you have some way that defines the way that that surface should look, and sometimes even move. And that code is shader code. So shaders are like, because of the way they work, is that they are absolutely ubiquitous. Like absolutely everywhere in games, you're going to find many, many different types of shaders that do all sorts of different effects. So I was thinking we could start by just like showing some examples of what that could look like in games, right? Because I feel like it's not very tangible to not have any like visual reference for this. So shaders are more like normal maps rather than diffuse textures. Shaders are completely unrelated to textures. Textures are input data that shaders can use if you want to, but you don't have to. So normal maps and diffuse textures are examples of data that we often use in shaders, but shaders are more about taking the information from textures or sometimes just other parameters or values or colors, and then running a bunch of math on that and then outputting it to your screen. A diffuse texture, for instance, is usually something that contains the color of the surface. And if you want to render an object where you have different colors on the surface and you want to define that using a texture, you can do that if you want. But you also don't have to use textures. In fact, most of the work that I've done in the past like 4 years have almost entirely been textureless because I don't know, I like math and I like doing things procedurally. And most of the games that I do tend to have an art style that doesn't require that many textures. So last night, I logged on to Final Fantasy and I took a bunch of screenshots because I thought this might be a good case study. Let's actually open a game, take a bunch of screenshots, and then just look at what is happening on the screen and how does this relate to shaders. So let's jump into all of my screenshots. I've been playing Final Fantasy all holidays, so I haven't been doing much else. So of course I'm going to continue doing things related to that. Okay, so let's open up some examples here. Okay, there we go. So this is a screenshot from Final Fantasy. And Final Fantasy, it's an MMO, and MMOs usually have a lot of like VFX and particle effects. As you can see in this case, my character is doing an attack. So there's this big like ring thing happening. There are impact effects on the screaming dog, where you have some wisps up here. And you can see that they're sort of arranged in a circular pattern here as well. There's another one here and another one here. And usually these types of things are a combination of particle effects and also meshes that have specialized shaders that run for like that type of effect that you're trying to achieve. So for instance, if we try to break this down and try to figure out like how is this whole thing constructed, right? We can try to think of, okay, so maybe this disk here, this could be a single quad, as in a mesh with 2 triangles, right? And then on top of that, you have like some sort of circular, swirly VFX type of thing, right? So you render that on that quad. And there are some like glowing vertical stripes here. This could either be a particle effect or like very small individual light strips. It could also be a cylinder mesh that simply has a texture that goes along the edges that gives it all of those glowy stripes, right? Same thing goes for the dog. You can see that there's all the rings here. That could be a single quad that kind of encapsulates all of the effects there, and then that has some sort of texture on it. The flare here, very likely a particle, probably also just a single quad with a flare texture on it. Same thing with this thing right here. And so forth. And you can sort of like try to break VFX down in this way and try to figure out, how is all of this constructed. And what shaders allow you to do is basically customize this in almost any way you want. So rather than just having textures, you can also animate these, you can blend them with other things, you can tell them to render additively, or they can multiply into the scene. So there are many, many different ways of doing this. So here's another example where the different particles use different blending modes. So blending mode is just a way of like saying, how should this combine with the background? So I can actually show you an example in Photoshop. You can see that this one kind of adds a glow whenever I draw with this blending mode. I can set a blending mode to multiply. And if we do that, it's going to multiply in, which in this case reduces the color values, so usually darkens, right? So there are many, many different ways of blending it. And then you also, of course, have the regular blending mode, which is usually just alpha blending or alpha compositing, where we're kind of like rendering something on top of something else. So these are very, very distinct ways of rendering something on top of something else, right? So we can like try to look at this. So how can we break this down? Well, we can see that there's like sort of an orange halo here, right? And that seems to darken the background. So we can presume that that is a multiplicative effect that is darkening that background. Then we can look at some of the other ones. It seems like the black ones here might not actually modify the background that much. So they're probably alpha blended, like the blue one up there. All the glowy white ones here are almost certainly additive, which means that they're going to brighten the background. Yeah, so those are different blend modes. When you say particle in this context, you're talking about engine stuff, right? The GPU shader code you see is a quad and it doesn't know what a particle, and it's just a mesh. Pretty much, yeah. So if we talk about like individual shaders, then shaders are generally what is dealing with each individual component of all of these things, right? So if we want to count how many shaders we have here, it is possible that this only has 3 shaders. It could be that it's kind of hard to tell without actually having the game at hand, but it could be that there's one shader that deals with the multiply, as in the multiply blend mode. And there could be another one that deals with additive, and there could be another one that does alpha blending. And then what can happen is that you use these 3 shaders, but you use them in different contexts and with different inputs. We're going to get into that later, how the structure of like shaders versus materials and all of that. Kind of going into too much detail here. I'm supposed to just quickly go through these. Okay, what else? Here's another interesting example. So this one has a refraction in it. Refraction is usually when you take some usually background and then you distort it. So if you want to have like heat waves above a road or something, then you can sometimes use refraction in order to distort some image. Underwater effects also use a lot of distortion, where you can see that the character is here and then there's a distorted version here. It's a little hard to tell how it works when it's not in motion, and I didn't have time to record a thing in motion. Here's another example when you like kind of mash all of these together. This is more about VFX than it is about shaders, I suppose. But you can do a lot of like fancy effects if you combine a lot of things together, right? So in this case, you can sort of trace out all the different disks you have here, right? There's one going here. There's a circular one going there. And you can see that with the combination of all of this, you can achieve a lot of effects, right? So if we try to break down the shaders of these, then again, we're probably going to look at one additive shader here for anything that's glowing. And then this looks like an alpha blended one for stuff that shouldn't make things brighter. This should just darken things, right? We want to blend toward the color of that we have defined in this probably particle effect, right? Another example of a lot of different planes. This is also something that sort of goes outside of what you do in particle effects. If you talk about Unity's particle effect system, doing something like this is generally pretty hard because particle effects usually deal with a lot of particles naturally, and they're usually kind of scattered and in many different places. But often you have cases like this where you have a very defined structure, right? Where you want to draw these like strips on the ground with a lot of these symbols. So these are likely 2 triangles, right, for each of these. I cannot draw a straight line. Anyway, yeah, so that's probably just a quad. And then you have another mesh that goes, it's sort of like the edges of a cube, very likely, that goes along here. You can sort of follow the shape, I hope. And then, of course, yeah, everything is triangles. So the mesh is going to be triangulated like this. So what the shader can then do, you know, the shader has the mesh that is this inverted cube with only the walls, right? And then what you can do then in the shader is that you have lots of textures you can combine in different ways. So you can see that there's this pink smoke-like effects. So this is very likely a texture that is mapped along this whole shape. There are some like multiply effects here that like darken the background that could be part of another render pass of this cube, I'm not sure, and so forth. So usually this kind of goes outside of what you can do with particle effects. This is more, you know, you have a mesh and then you want to make it look a very, very specific magical way. And that is something you can do with shaders. Okay, should I go through more examples or is it boring you at this point? I probably took too many screenshots. Same thing here. It's a big ground texture. A lot of like additive glowy effects. There are these little daggers pointing into the ground, and all of these are probably also just simple quads and stuff, right? This became a VFX course now. It's not about shaders anymore, it's about VFX. Oh, here's a good one. You can even use shaders in UI. So this is an example of a progress bar that sort of has this mask on top of it in order to have all of these symbols. But what's happening underneath these symbols is that there's a progress bar that's going to render inside of these. You can see that it's halfway filled here, where it's sort of going up to this point. So this is also a very good use case for shaders. You can make a single shader that, you know, renders this thing. And then you have input data that says how, like, what is the percentage of fill on this bar, right? And then using that, you can then just define exactly how you want this to look, depending on how much you've stored in this bar, right? Same thing goes for, like, a lot of MMOs have like markings on their icons. So these little dashes around the edge here, they are also animated and move around in a circle. You could do that using a shader. There are lots of like circular progress bars you can also define in a shader. Or you can do it with sprite sheets. Usually makes things easier than custom shaders for everything. Here's a more render pipeline related one. So shadows. If you want to make shadows in a game, that also requires a lot of processing on the GPU. Because quite often your GPU needs information about everything in the world in order to cast shadows like this, right? So if we look at this scene, most of the background is pretty well lit. There are some shadows here in the background that are cast here. But there's a building here that is casting this pretty complex shadow, right? Because it's following the shape of the edge of the roof of this building, right? And it also like casts realistically on top of all of these objects. So that continues there. And then even for dynamic shadows for the character, there's shadows going underneath there, shadows going across here, going all the way down there, right? And this is another process that you tend to do on the GPU. And there are many different ways of doing shadows, but it's kind of interesting that like some of the techniques you use to cast shadows is that you kind of render the scene from the point of view of the light source, and you only render how far away geometry is. And then you can use that information in your usual frame that you're rendering here in the game to know whether or not shadow or light is going to hit a certain point or not, right? Here's another example. The skin is a pretty difficult thing to render, it turns out. Skin has a lot of properties that generally most like solid objects in the world don't have. So one thing that you might notice when skin is rendered in some game is that usually there's some highlight where the light source is hitting, right? this is the highlight on the cheek. And then you can see that it sort of fades to shadow in this direction, right? And then you have a shadow line here, right? So one thing that skin has, which is a very like specialized thing, is usually called subsurface scattering. Subsurface scattering means that light sort of enters something. So if you have a surface, you have light rays coming in. In many cases, if it's a perfect mirror, light would just bounce off of it, right? But in some cases, light can actually enter, and then the light can scatter around inside of some surface and then hop out somewhere else. What happens is that usually some wavelengths are absorbed when this happens. So it could be that you have white light coming in, but then once it starts to scatter inside of the skin, some wavelengths are absorbed, and you can get a more red tinted light coming out of it because the greens and the blues have been absorbed, so mostly red is coming out. So quite often with skin is that you get this red tinted shade here that happens in the transition where you get less light, but then the scattered light keeps spreading out of that. You don't need to know how to do all of these things. I'm kind of just going through of like what you can do with shaders and some examples from, in this case, from Final Fantasy. And then there are all sorts of properties of all of these surfaces, right? For instance, the lower lip has a very glossy highlight here, right? But the cheeks don't. There's not a glossy highlight here, or on the nose, or like nothing like that, right? They're pretty matte. So all of these things are things you need to define in the shader. Where do we want things to be glossy? Where do we want things to be matte? Where do we want to have subsurface scattering? And so forth. Let's see, what else? Oh, hair rendering is surprisingly difficult. But I don't know if we should get into all of the details of that. Here's another good thing to talk about. Someone mentioned normal maps before. Normal maps are kind of a way to add more geometry data, or what looks like geometry data, without actually adding geometry. So quite often, you're making meshes with triangles. So we can try to like sort of work out what the mesh looks like here. This is a pretty low poly mesh, right? You can see that it's very jagged, but the internals of it looks pretty detailed, right? It looks like a pretty smooth curved surface. All of these intricate details look really nice. But what the geometry likely looks like, if I were to guess, is that I would probably have a very, very simple structure. Actually, I could see that one now. I'm guessing it would be something like this. So it's sort of just like a very simple low poly cone, but with certain textures, you can make a normal map which encodes data about the direction that a surface is pointing. And with that data, we can make it look as if it's being shaded, as if there's geometry there. Same thing goes with this. This doesn't actually exist in the triangle data, but if we have that encoded into a texture, we can then use that texture in order to get more detail out of it, instead of just adding geometry all the time, right? Especially in like an MMO, where you're gonna have to have like a lot of characters in one place, and adding geometry detail that's like super, super high poly to that is not going to work out well, right? So you need some shortcuts to add more detail where there is none, right? So we're going to do normal maps probably on Thursday, I think, depending on how far we go. All right, let's see. Let's switch game. Overwatch. What a game. So we can see sort of the same concepts here. Like regardless of what game we're looking at, we can almost always just take a screenshot and then sort of break down what's happening in the frame. So Overwatch is kind of interesting in many ways. One thing that Blizzard tend to do in their games is they have a lot of like specialized shaders in their UI. So this glow, for instance, is sort of like an additive particle effect, but it's in your UI instead of in the world. And then obviously in the world, there are tons and tons of different particle effects. You have like Roadhog's gun. You got like an additive thing here. And I can't draw for some reason. Oh, I'm drawing underneath. Great. And then you have the Reinhardt's barrier. This one looks like it's very glowy. Could be additively rendered. And then you have some refraction here again. You can see that there's like a distortion bubble here. It might be hard to tell on stream, but you can see that it distorts this path here. There's a smoke trail coming here that also gets a little distorted. What else? We have Tracer, just did a blink thing, maybe reverse. I don't know which effect this is. This is probably the teleportation thing. So you can see that Tracer is rendered completely differently here, right? So very likely Tracer's shader has just been completely swapped to some other shader, right? Everybody else is rendered like with their normal textures and whatnot, but Tracer in this case has an entirely different one. And this particular type of shader is usually called a Fresnel shader. Fresnel is an absolutely ubiquitous term that you're going to hear about too much. F-R-E-S-N-E-L, because yay, French names. Fresnel. So what Fresnel basically means that as something is starting to face away from you, you get a stronger light. So you can see that the edges are kind of lit up here, right? But the middle is not lit up. So it's almost an outline effect, but it's not actually an outline effect. And it's kind of important to know the difference between the two. Right, another example of Fresnel, Roadhog in this case is being frozen. And it's probably a little bit more visible here to see how it works. So you can see that if you look at his hand, for instance, stuff that is kind of directly facing the camera, in which case like this part of the thumb does not have this glowy effect. It only starts happening for surfaces that are facing away from you, right? The Roadhog's hook here, for instance, is also facing away from you more so than this part of the thumb, and therefore it's brighter, right? And this part has a very, very steep angle, so this whole thing is very bright. So this is a very useful, simple way of getting a sort of like outline effect, highlighting objects, and so forth. Another one, Winston's shield, similar thing. This shader also has some like extra features for, because this is a spherical bubble, but it can intersect with the world in different places. So it intersects with the ground here, and then it makes it so that there's a bit of a light going around that edge. So it like kind of follows around the whole bubble. It also intersects with the world up here, right? So even though it's intersecting with a pretty complicated geometry here, it can still maintain to do this like whole outline thing. Yeah, usually that's done with like depth hackery and whatnot, but do Fresnel have relations with rim light, or am I confusing them with each other? They are usually related, but they're not the same thing. There are all sorts of things that are called Fresnel. If you start reading up on like physically based shading, you're gonna find the word Fresnel in terms of like physical light propagation, which is slightly different than the artistic usage of just a Fresnel shader. Yeah, but the idea is that as the angle towards some surface versus the camera is very low, something happens, right? We're going to make a Fresnel shader later, so we can see it in action if you want to. Here's a screenshot from Demon Souls. And you might tell that there's a bit of a highlight effect on the character. This too is Fresnel. Everything is Fresnel. Fresnel is everywhere. No matter what game you're getting into, there's going to be Fresnel somewhere. Exactly the same effect. You get like a glow around the edges, and as the surfaces are pointing toward you, that glow sort of disappears and it fades to darkness. Yeah, so it's the exact same principle. It is important to note though that Fresnel is kind of only like, it works best for surfaces that have relatively smooth surfaces. As soon as things get sharp, you don't really get the same outline effect. As you can see, the shield here doesn't actually really have that type of highlight, not even close compared to like around the knees here, right? So they're a little bit separate, but it's this very, very easy hack to add to your stuff. And it also looks a little different than an actual outline effect. This is a game, Return of the Obra Dinn. A very, very different usage of shaders. We're being sort of looking at more VFX and realistic stuff. This is another game that is heavily using shaders, but for an entirely different artistic purpose, right? So the Return of Obra Dinn is a game that is only using two colors. Well, it's not exactly black, but it's pretty much just black and white. And then in order to express shading, they use dithering in their game. So Yeah, so like this is something that you can do with shaders too, and like this is like perfect for shaders because they deal with these types of like graphical things, and then you can yeah, do all sorts of artistic effects like this. Another example is something less realistic is Kentucky Route Zero. This is one of my favorite point and click games. It's super nice and atmospheric. Kentucky Route Zero also has a very like minimalistic art style, but even though it's very minimalistic, there are lots of places where they use shaders for artistic effect, right? So in this case, you can see that they're playing a lot with depth in this one, because if you look at the trees here, the bird is in front of these trees, but the fog implies that these parts are in the background. So this is a like very like it's a trippy effect. It's a trippy game that employs all sorts of like graphical things to achieve their like artistic vision, right? And you wouldn't be able to do this if you were just using like Unity's built-in shaders, right? So really what shaders are about is allowing you to expand your visual horizons, right? I thought that was sorting of the sprites. All of this is dynamic, and so if you move the camera and the geometry, it's kind of difficult to do this without like coding that into the shaders, but maybe you can do it with just sorting as well. But regardless, setting sorting on something is dealing with the graphical aspects of this, which is dealing with shaders, right? That was a very long just walkthrough of random shit in games. Oh, actually I had a few like separate examples. Here's an example from a game that I worked on, made in my studio, NeatCorp. So this is the portal locomotion system in Budget Cuts. So in this case, this one has a very specialized shader for dealing with opening up this portal, right? So you use this portal to move between locations and rooms. That's pretty much what this does. So you can see that you open up a portal into a different room, and then this renders into that portal that's sitting in your hand. And then you can still see anything outside of that, right? And yes, this is a VR game. And then when you teleport, this bubble sort of expands and encapsulates your entire field of view. And then once it's encapsulated your field of view, you're standing at the new location. And we wanted this to, of course, be like a completely seamless experience. So we didn't want to have any jarring like flashes happening, or, you know, we didn't want to approximate this either. We wanted it to be, look exactly like you're just like smoothly moving to the new location, right? Is it a second camera with a render texture? It used to be, but it's not anymore. Because turns out having a like rendering things in VR, you generally have to do things very high resolution because you have you need a lot of pixels for it to look good because you have a very wide field of view when you're wearing a VR headset. So you need a lot of pixels. It's usually a higher resolution than 1080p or whatever. And if you want to have another render texture for the portal, that usually means that you're going to have another full screen render texture, which is a lot of memory, especially if you want to like target the lower end platforms. Here's a very simple example. This is from another game I'm working on called Flowstorm, with this little rocket here. So this is another VFX shader. It's this rocket flame is a single quad. It's two triangles. And then everything else is done in the shader. So you can see that it's sort of bending when the rocket turns. It changes color when you stop or start accelerating. Yeah, and then the little flakes, that is a particle effect. But everything else is done in the shader itself. A water shader I made for another game at NeatCorp. So that game is very stylized. So in this case, I wasn't like aiming for realistic water whatsoever, but I wanted it to look really colorful and yeah, very lush and pleasant to look at. So then you tend to want to get these like, you want to have a little foam ridge along the edge. You want to have some cute specular highlights, and you want to have this gradient that goes from like tropical cyan and then down to the deeper blues, right? Here is not my shader. This is from Uncharted. Uncharted and the team working on Uncharted have like some of the best technical artists out there. So usually if you want to look at really high end like AAA shaders, they do really good work there. So this is a lot of things are happening here, of course, but the surface of the water is going to be one shader. You have some particle effects for all the smoke there. There's even a rainbow. Like there are lots of things happening. But this is again stuff you can do with shaders. Oh, and the rocks as well. We haven't looked at boring objects, but all the boring objects have shaders too. I'm mostly talking about the more like exceptional cases that you can't really do you know, only using the built-in shaders, right? Okay. All right. Any questions so far? I guess there's nothing to ask about. I just mentioned that shaders exist in games. Does the portal shader have a field for position of the current portal, and then it just renders stuff from that position in a circular viewport? The way that it works right now is a little complicated to explain, but generally the easiest way to explain it is you have a player position, right? You have the cameras that are rendering for the player camera, where the head of the player is, because it's VR. So you have the camera for your head, and then once you place the teleportation beacon somewhere, we create another set of cameras that mirror like where your head would be if you were to teleport, right? So then we have two sets of cameras. And then what we do is that we render the first set of cameras, and then we do some depth buffer hackery, and then we render the second ones on top of that. So there's no render texture, it's all just the frame buffer, but it ends up just working out. Has a lot of weird side effects though, because depth buffer hackery kind of breaks a lot of things, but it worked out. How often does someone need to code a shader compared to an artist making a shader using nodes? That's a good question. It's hard to like distinguish between the two, because quite often you can have coders just making it using nodes as well. Right now, whether or not you should make things with a node-based editor versus writing things by hand, in Unity at least, is more determined based on whether or not you're using specific render pipelines. If you use the built-in render pipeline, you're most likely going to write shaders by hand or use like a third-party shader editor like my old ShaderForge or Amplify shader editor. If you're using the Unity's new URP and HDRP render pipelines, then you're probably going to use Shadograph for those, right? But it kind of depends. I mean, if you have a team of a lot of artists that can make shaders and node-based editors, then that might be a really good advantage, because quite often shaders live in this sort of weird territory of it's very technical, and yet it's also very artistic and visual, right? It feels like the most low-level front-end code you're ever gonna do, because you're like very, very much doing like extremely low-level operations, and yet it's something that is like directly going to be visible to players, usually. Not always, but usually. Are there certain tools for making maps like normal or displacement maps, or do you draw them by hand? There are many different ways of doing them. You can either generate them, you can either sculpt them. If you're using something like ZBrush, usually you sculpt a model, and then you can export a normal map from that. And then you can have a low poly version of your mesh that then uses the high poly's normal map. That's a very, very common workflow for like AAA style realistic graphics and whatnot. You can also do 3D scanning. You can literally do photogrammetry scanning of different surfaces or even entire models, and then export like texture maps from that. What can you use to generate them? You know, I haven't generated them for a very long time. I don't know what. Generally, if you take like a color texture and generate a normal map out of that, you usually get very bad normal maps. I'm sure you can find tools online for this. There used to be one a really long time ago called Crazy Bump. I think XNormal is something that artists use a lot, even though XNormal looks like it's from years ago. I don't even know how many decades ago it looks like. XNormal has a very Winamp aesthetic. Anyway, XNormal is very, very commonly used for baking normals, like taking a high poly model, generating a normal map, and then using it on a low poly model. Substance Painter is a pretty good program for stuff like that. Yeah, so there are a bunch of like procedurally, or like Substance Designer is a really good tool for generating textures. It's really, really neat. You can do all sorts of like procedurally generated stuff, then export, you know, all the maps you want from that, like height maps, normal maps, specular maps, gloss maps, metalness maps, and whatever. Oh, and albedo maps. There are all sorts of like procedural tools like that. There's also, like you mentioned, the Substance Painter, which as far as I know, I haven't used it that much, but I'm pretty sure it's a tool where you can sort of draw on the mesh, and then that you can draw directly into the texture on the mesh itself, rather than using a flat texture, right? And then it has all sorts of like procedural things if you want to like add weathering to it or add rust to some object or whatever. It's very easy to do that using the tools that Substance have. Artists often can't or don't make shaders unless they're technical artists, right? It's a matter of definition, I suppose, but usually the capital A artists who just do 3D modeling or 2D art generally don't do shaders. Quite often there's, you know, a specific role in game development where someone is a technical artist, and the technical artist is then responsible for creating those shaders. And then usually you need to make sure that the communication is good, because not all technical artists are good at art. So sometimes you need to have like an art director or even other artists to like guide them on like exactly what they want to achieve, right? How do you learn about the various types of shaders? Like, where does one even encounter the Fresnel thing in the first place? Good question. I guess a lot of like looking at existing games and Googling for how to achieve certain effects. I don't really know how I learned about it the first time. Probably it was my teacher a really long time ago. Yeah, I don't know. Listen to me. There you go. That's how you encounter these effects. You're in it right now. This is the way. But you can probably find like some website that has like a repository of like different shader effects and whatnot. Fresnel happens all around you IRL constantly? Yes. Although, yeah, it depends on what type of Fresnel you're talking about, but the light effect of the Fresnel effect, yes, that happens a lot. I don't know if it's possible to show it on stream. Okay, maybe this thing. Maybe. Okay, you might be able to see that the top of the outer edge of this thing right there has a bit of a glow to it, right? And the idea is basically that almost any surface, when you get to a low angle enough, oh, actually, you can't see my fingers in a reflection on this object, right? But if you go really low, you can see some reflections off of this, right? So the idea is that if you have a very, very, very steep angle looking at a surface, it becomes more reflective. That's the more scientific light version of the Fresnel effect, which you might want to separate from the more like unrealistic, glowy Fresnel effect that people usually add to like highlight objects and whatever. Reflections on a water surface might be a good example for Fresnel. Yeah, water is a pretty good example of that. Usually pretty hard to find good pictures that shows you both the transparent part and the reflective part. I had one in a presentation at one point. I mostly find like fake ones and renders that are like not super good. Here's a pretty good example. So it's kind of difficult to see here, probably on stream, but it's way more transparent here, right? You can sort of see the stuff underwater. But then as you go to a more like raising angle, like a very, very sharp angle, there's like a very, very like mirror-like reflections, right? So that's the Fresnel effect in action. In this case, there's sort of a trade-off of like, you know, how much of the light do you see that's reflected off of it versus the light that's coming out from underneath it, right? So now we mostly talked about like what you can do with shaders, some vague effects of like, you know, what you can do in like different types of games and what some effects are called, but we haven't actually gone into like how to make shaders. This is all very like theoretical. So let's get closer to the practical reality of making shaders in Unity. So usually there's a bit of a like terminology mess when it comes to shaders, because when someone says a shader, that can mean many, many different things, unfortunately. So I'm gonna try to break this down, the structure of a shader works. So we can start with the .shader file, right? So we have a shader here. So now we've got the Unity file of a shader. So what does this contain? Let's break this down. A shader has properties. Properties are basically a set of input data. So this could be like colors. It could be just values that you use for like, maybe it's a number for the amount of health you have, and then you want to render a health bar using that value. This could be textures. And then indirectly, you don't pass this with the property, but indirectly you also pass the mesh that you're going to use, right? So the mesh that's going to be rendered is usually passed into it. And then you also have the matrix for that mesh. Not always, but usually. So the matrix contains the transform data of where it is, how it's rotated, how it's scaled, all of that stuff, right? So these would be actual properties you pass in, and these are kind of implicitly passed in from, you know, whatever object you have in the game, right? All right, so we have a shader, a shader file. The shader file contains properties. All right, what else? So properties is just the input data, but not the shader itself isn't here yet. So then the next level is a subshader. So a subshader, you could just call it a shader. It's kind of confusing. But the way that things are set up in Unity, at least, is that you can have multiple subshaders in a single shader file. So a use case for this is that you might have a subshader that is meant to be a little bit more optimized to run on like low-end platforms. So if you have multiple subshaders, you can make it pick the one that's appropriate for your current situation, right? But for our purposes, we're not going to make multiple subshaders, so you might as well just consider it a shader. The subshader itself contains something called a pass. This is a render pass or a draw. I don't really know what you want to call it, but we can just call it a pass. And subshaders can contain multiple passes. So you can have multiple passes in here. There are lots of shaders that are not multiple passes. Usually you do that if you're doing like certain types of lighting. You sometimes want to have multiple passes or very, very specialized VFX. But usually you just have one pass. So usually it's a relatively straightforward path going from, shader, subshader, pass, and then you can start writing your shader code. So inside of the pass, this is where the actual shader code is happening. You can break a pass down into many, many different types of shaders, but usually what you're going to be using is a vertex shader and a fragment shader. The fragment shader is sometimes called a pixel shader, but it's a bit of a misnomer, so fragment shader is the technically correct one. If you're going to search around for this, you're going to find people calling it the pixel shader. But yeah, so this is the kind of the basic structure of a shader file in Unity. So if you're wondering like where is the shader code here, then what this is that this part, the vertex shader and the fragment shader, that is the part that is going to be written in the shader language HLSL. I think it's high-level shading language or something like that. So that's the actual shader code, right? Everything outside of that, as soon as you get into the passes, the subshader, the properties, all of this is kind of Unity's own syntax for like defining where should this happen in the render pipeline, should this have some sort of properties, some input data, and all that stuff. All of that is called shader lab. So sometimes it's useful to distinguish between shader lab and HLSL if you want to like, sorry about my bad handwriting. So all of this is pretty much shader lab, like all of this, the part in white. Okay, so the actual shader code you're going to be doing is a very specific part of the shader. The red part here is the fun part. The white part is the boring part, because the boring part, this is mostly about figuring out how the heck do shaders work in Unity, how do I access X, Y, and Z stuff, and there's usually a lot of like boilerplate involved here. But this is pretty much the basic structure of a shader. Okay, so what do all of these things do? So like, what is the difference between the vertex shader and the fragment shader, and what are they used for? All right, so let's see if we can break it down. So we have all of these properties, right? We have the colors, the values, the textures, the mesh, and the positioning data. So all of this is going to be an input to a shader code that is then going to run, right? Let's start with the vertex shader. Let's go. There we go. Vertex shader. Perfect. Vertex shader basically takes all the vertices of your mesh, right? Because when you're rendering something in a game, you usually do that with a mesh, and meshes are built out of vertices and triangles, right? So you have all of this data that is coming into the shader. You have some mesh, maybe it's a cube, maybe it's an entire character. It could be many different things. But the point is, whatever you render in a vertex shader is going to be composed of lots of vertices, right? So what the vertex shader does is it's kind of like a for each loop over all of the vertices that you have. And then you can access data from all of those vertices. So you can think of the vertex shader as a for each vertex, right? And then all of your vertex shader code lives here. So you can define all of these operations on every vertex. In most cases, what you want to do in the vertex shader is that you want to put these vertices at some place in the world, right? So if you have an object like, I don't know, let's say you have a cube, right? This is not a very good cube. You want to put this somewhere in the world. But one problem is that the vertex shader doesn't really want you to put things in world space, and not in local space either, and not even in view space. The vertex shader wants you to say, where are these vertices going to be in what's called clip space? And clip space is kind of like a normalized space from -1 to 1 inside of your current view or render target. So usually it's kind of a like weird transformation where you jump between like 3 different matrices. But generally, there's a very, very simple way that you do that. You basically take the local space coordinate of all of the vertices, and then you transform that using what's called an MVP matrix to then convert it to clip space, and then you're kind of done, right? But what you can do in here is that you can modify the vertices if you want to. But yeah, the usual case is that you don't modify them, but you can do that if you want. That's the vertex shader. What was tangent space now again? We're going to talk more about that later. I could go into it now if you want to, but I first want to talk about the general structure of the shader. Okay, so we got the vertex shader here. So I'm going to try to do this chronologically. All right. Like someone is mentioning, the vertex shader is often used to do like animating water or doing stuff like leaves that sway or like grass that can sway in the wind. Because then what you usually do is that you define some math in the vertex shader that makes these move in a certain way, right? Because you can set the position to anything, right? It doesn't have to be where the object is even, right? Or the acid shader, yes. If you want to do the acid Minecraft one, you would put these things in some wild location that would make it look trippy, right? Okay, so you got the vertex shader where you are going through all of the vertices and you can do whatever you want there, right? As long as it's a per vertex thing. Should you manipulate vertex UV coordinates in the vertex shader? Generally, yes. You can do it in both the vertex shader and the fragment shader, but it depends. Like, can you do it in the vertex shader? Then almost always do it in the vertex shader. If you can't, you have to do it in the fragment shader, right? Okay, so we got the vertex shader and now we're moving on to the next stage. There is some internal magic that happens here on the GPU. So what's happening here is a lot of stuff related to the depth buffer. It's going to do like a rasterization step where, it knows the position of all the vertices, and then it's going to try to translate that into, what pixels go where, according to where you place them, and so forth, right? So there's a lot of like internal stuff happening between these things. Okay, but after that's done, you can now go back to your code where you can start defining things on your own. So now we get to the fragment shader. Okay, so now in the fragment shader, just like the vertex shader was kind of like a for each loop over every vertex, the fragment shader is a for each loop over every fragment. And the reason it's called fragment and not a pixel is because pixel is usually 1-to-1 corresponding to a pixel on your screen. But in shaders, that's not always the case. So usually you use the word fragment. But in most cases, it's kind of the same thing as pixels, right? So it's sort of like for each pixel inside of all the geometry that we're now rendering, we're going to run some code. Okay, so the fragment shader, basically all you do is you set the color of every pixel. So what color is this going to be? Well, that's up to the fragment shader. Maybe it's going to be red, maybe it's going to be green, maybe it's going to be something else entirely, right? So the fragment shader basically iterates through all of the fragments or pixels that are going to be rendered, and you can write code to define exactly how that should look. And there are all sorts of ways of doing that. This is where like everything sort of happens, where you can make it look exactly the way you want. But yeah, this is the basic structure. And this is usually the limitations you're also working under, right? Because this is a relatively limited structure where you need to do things one at a time, right? The vertex shader always happens before the fragment shader and so forth. And there's not really any communication in two ways, like back and forth between these. There's only a one-way communication from, you can pass information from the vertex shader to the fragment shader, but not vice versa. Okay, so the fragment shader, you specify color, glossiness, specular, fresnel, etc. Vertex shader is only the shape of the object. Yeah, so the vertex shader, all you do there is either set the position of vertices, or you pass data to the fragment shader. That's kind of it. That's all you do there. But sometimes you want to have very, very specific data that you have like pre-processed in some way before you pass it to the fragment shader. A good example is if you want to manipulate UV coordinates, but we're going to get into that later. But yeah, so basically, this is setting the pixel color. And that's it. It literally returns a color. Oh, I didn't distinguish between shaders and materials. That's also important. Let's do that. So generally what we're talking about here, this whole thing is the code that you define in the vertex shader and the fragment shader, which lives in a pass, which lives in a subshader, which lives in a shader file. So there's a lot of like nested things in a shader. So sometimes it's good to like make sure you can keep track of all of this stuff. You can think of all of these things as input data to rendering your object, right? The green ones up here, these are usually called properties. They are properties that you can configure before you're rendering your objects. And then there's some extra data for, you know, the mesh you're going to render and the transform of that mesh itself. These things are usually like automatically supplied by your mesh renderer component. But these properties you have to define yourself, and usually the way that you define these properties is using a material. So the material itself contains explicit values for all of these different parameters that we can input to our shader. And the material also has a reference to the shader. So you can never, quote unquote, add a shader to an object in Unity. In Unity, you apply a material to an object, and that material then has a reference to the shader itself, right? So you can sort of think of materials as pre-configured parameters to be used when rendering something with a shader, right? So to clarify, you can have multiple materials that all use the same shader, but they have different input data, which is very, very common. Say you have a shader that renders, that has a single property of a color, then you might have, you know, two materials that both use the same shader, but one of them has the color red, the other one has the color blue, or whatever, right? So let's look at shader code. Let's get a little bit more practical. So there are many different types of shaders you can create in Unity. Since this is a course for coders, I want to start with sort of the simplest, most low-level thing, because I think it's good to get a grasp of like how shaders are structured, and I think the best way of doing that is to use the unlit shaders in Unity. There are many, many different types of shaders, especially if you go into the different render pipelines and if you use shader graph and so forth. But for now, we're just going to make the simplest unlit shader. All right, I don't know what to call this. Shader1. There we go. Perfect name for a shader file. Okay, so let's see. All right, there we go. Here's a default shader. And I'm going to fix all these brackets because they annoy me. All right, so you can see that we got the shader itself, and then we have the properties. So again, the properties, this is the input data, excluding the mesh and like maybe lighting information and all of that stuff that Unity automatically supplies. So that's kind of your own defined input data. Then you got the subshader itself. The subshader contains a pass, and then the pass contains your actual shader code. So anything inside of the CG program and end CG, that's part of the shader code. It says CG. Unity is practically HLSL, but you can call it CG as well if you want to. Okay, let's see. I'm just going to fix some more brackets because I don't like these brackets. All right, we can go through this line by line if you want to. So both the subshader and the pass has a bunch of tags and things you can like specify in order to define how this object should render. So the subshader has stuff when it comes to like sorting, you know, is this object opaque? Is it transparent? Do we want to change the hue of this so that it renders before or after some other shader? That's the type of stuff you set in the subshader. In the pass, you set the more like explicit rendering stuff for this render pass itself, such as the blending mode. You can set the stencil properties and so forth. So subshader, usually it's more render pipeline related, and pass is more like the graphics related stuff for this specific render pass. LOD 100 is a specific thing that you can use to, I think you can set a LOD level of an object, and then it will pick different subshaders based on what you set LOD to. I have personally never ever used this, so we're going to delete that. No more LOD. All right, CG program. So this is where the shader code starts. And then we have pragma vertex vert, pragma fragment frag. This is just a way of telling the compiler what function is the vertex shader and what function is the fragment shader. So basically we're saying that we want our vertex shader to be the function that is called vert, right? Which is this one down here. And we want the function called fragment to be our fragment shader. So this is kind of just like pointing to the name of these functions to say that this is the functions we're going to use for these two shaders, right? We're going to ignore fog, so I'm just going to delete everything related to fog. That's gone. Include unitycg.cginc. This literally takes code from a different file and pastes it into your shader. So unitycg.cginc is a file containing a lot of the Unity specific things that you might want to use in order to like do things more efficiently. There are lots of like built-in functions there. It's a very useful one to include. Yeah, you pretty much always have that there. You can also have your own things included if you want to include a math library or something. I don't have a math library for shaders to pitch. God damn it. Okay, so now we're on to the more specific shader code stuff. So app data. I hate this name. I think app data is a terrible name for this structure. So we're going to rename this mesh data. There we go. I'm going to use capital M. You don't have to follow along, by the way. Like you don't have to write the same things that I'm doing. Just a heads up. So I might go a little quickly because I'm not like expecting you to do the same thing at the same time. All right, so I'm going to call this mesh data. This is a structure that we're going to run into later. So this is a bit of a weird order for all of these things. I might move things around a little bit. Okay. So then you can define variables for your stuff. I think they're sometimes called uniforms. But basically, if you have some property, in this case it's a texture called main_text, you also need to have a variable to define along with it. It's a bit boilerplatey and annoying. And texture is a little bit complicated, so we're actually going to delete that. We're not going to use textures, so I'm going to replace that. So let's say we want to have a value, which is a single float value, right? Let's see, I always forget the syntax. Okay, so maybe we want to have some value. We give it a name in the inspector. So usually that's something readable, that's not like, I don't know, you usually want to make this very like user-friendly and whatnot. And this is the internal variable name. And we want this to be a float. I want to set this to some value, some default value, right? So now we have defined a single float property. So if we make materials, we can then specify different values here for all of the different materials. Float 4 for vertex position. Yes, usually it's float 4. I actually don't know if the fourth component is used for the vertex position there. I'm not entirely sure. There are lots of cases where you do use the fourth component though, but I don't think it's used here. But quite often when you're dealing with mesh data, quite often everything you input is a float 4 regardless, because that's sometimes the data you have from meshes are called vertex streams, because usually or quite often you're kind of using UV channels for stuff that's completely unrelated to UV mapping when it comes to like textures and whatnot. So pretty much what it is, it's just a bunch of data coming in from the shader, and they're always defined in clusters of 4. So that's why it's a float 4 in almost every case. So if you're doing like lots of like procedural generation and whatnot, then quite often you just have float 4s and then you write float 4 data into that. But we're getting ahead of ourselves. We're not there yet. Okay, I'm removing the texture stuff because we're not going to get into textures yet. So we defined a property, and then in order to use that property in our shader, we also need a variable to go along with it. So I'm just going to do float value. And then this is automatically going to get the values from the properties in the shader, right? And yes, autocomplete and syntax highlighting for shaders is absolutely garbage. And it's only very recently that this is starting to get better, which is why I recommend using Writer for this, because Writer does have good syntax highlighting and whatnot. Okay, so now we're going to the mesh data structure. So the mesh data you're getting here are always per vertex. So this is the per vertex mesh data. So this is the vertex position, if I can spell. And in this case, this is going to be the UV coordinates. UV coordinates are incredibly general. You can use UV coordinates for almost anything. It just so happens that quite often they're used for mapping textures to objects. So if you have a, let's see, if you have a cube, for instance, and you open a UV editor, let's see if I can remember where to open it. There we go. You usually have some 2D coordinate system where you are defining where do we want to map a 2D texture onto this 3D object, right? Which is kind of a complicated thing because you need to unfold this whole thing. You need to define where all these things should go. Usually you need to like pack them in ways that are like smart. It's a lot of work, like just doing UV mapping and like making that good. But yeah, okay. So what is happening here? We have float for vertex. These are variable names, so we can name these whatever we want. They could be just whatever. But the colon here is called a semantic, and this is the thing that tells us, or tells the compiler, that we want the position data to be passed into this field. Text chord 0 refers to UV channel 0, which is usually the first one. And then you can continue doing this if you want to. Text chord 1 would be the UV1 instead of UV0, and so forth. There's only a limited amount of things you can get out of this. Quite often, the things you're going to use is UV coordinates. Position always has to be there. And then usually you have normals here. So if you go to, let's create a plane. This one has a bunch of vertices. And oh, it's probably up here. Display, polygons, normals, vertex normals. There we go. Okay, so if we take a vertex and move it away a little bit, you can see these green lines, right? So this is the normal direction of this surface. So if we change the direction of this, you can see that the normals change along with them, right? So this is kind of the direction that the vertex is pointing, which is usually used for shading and whatnot, to make things look smooth or to make things not look smooth and so forth. So you can see that if we make a little bump like this, you can see that the shading makes this soft hump here because it's interpolating these normals across the faces. But the normals themselves are defined on a per vertex basis. Yeah, so when we refer to normal, that is the normal direction of a vertex. And there are all sorts of like other things you can get here. You can get, for instance, you can get the vertex color, which I believe is just color. I could be wrong. I haven't used vertex colors for a long time. And there's another one where you can get the tangent direction. And tangents are crucially float 4s, and the fourth component actually contains important information. So all of these are like useful whenever you're doing, whenever you need data from the mesh, right? But if you just want to do a simple like apply texture to mesh, then pretty much all you can do, or all you need to do, is have your vertex position and the coordinates you want to apply the texture with, right? But you don't need to use UV coordinates in order to use textures. UV coordinates is just one way of like getting a coordinate system for your textures, right? How do we know if we need a float 2, float 3, or float 4? That depends on the data. It kind of like a normal direction is a 3-dimensional vector. So it's naturally a float 3. A tangent in Unity specifically, this might be a more universal thing. In Unity, the first 3 components is the direction of the tangent, but the 4th component contains sign information, as in whether or not it's flipped or whether or not your UVs are mirrored. So it's just a kind of a hack where the W component just contains sign information. The vertex color is always float 4. If you have colors anywhere, float 4 is always RGBA. And yeah, UV coordinates. Oh, what's the difference between UV channels? Nothing. The difference between UV channels is what you define them to be, right? So a common thing that you do in games is that you might have UV0 might be for your diffuse, normal, map textures. So this might be the coordinates for your, like all the texture that you apply to the surface. UV1 coordinates, this might be the light map coordinates. So sometimes you have like different coordinates for different types of textures, and light maps is another one of those textures, but quite often you want to have a different layout for like color textures versus baked data like light maps. For instance, if you UV map something, like sometimes you have a lot of overlapping overlapping shells because you want to use the same texture for the same place or for different places on the mesh. But if you want to encode light map data, you can't have overlapping UVs, right? Can meshes include multiple UV channels? Yes, you can have many UV channels. And if you want, you can make them float 4s. So if you're doing procedural generation, you can just shove data in there. So quite often, the UV channels are just data. And then how you use that data is up to you. But all it is a float 4 associated with that vertex, right? So it's like having a UV map placement for each map you're using. Yeah, you can use it that way if you want, right? So that's the mesh data. We haven't even gotten to the vertex shader. I feel like I'm doing this way too slowly. Okay, V2F. This is Unity's default name for the data that gets passed from the vertex shader to the fragment shader. I usually like naming this something other than that. So something like fragment shader input. We could name it Interpolators. If we want, that would be pretty accurate. Let's go for Interpolators. Okay, fog. We're going to ignore fog. All right, so this looks very similar, but it's pretty different in terms of what this is going to be used for. Interpolators is the way that we pass data from the vertex shader to the fragment shader is using this structure. So everything we're going to pass to the fragment shader from the vertex shader has to exist inside of this struct, right? So you can see the vertex shader returns interpolators. So in this case, we're passing UV coordinates and the position here. Again, there are semantics here. The semantic SV underscore position, this is the clip space position of this vertex. Or the clip space position. It's a little weird to say for this vertex because of reasons I'm going to get into later. But so that's a clip space position of each vertex. And then the UV channel, this could be any data you want it to be. In this case, text chord does actually not refer to UV channels, which is really confusing. But in this case, if you want to pass data, you can just jam a bunch of text chords in here. And what you write to these channels is entirely up to you. And they don't have to be UVs. They could be absolutely anything. As long as they are float, whatever data type you have. The maximum one is float 4 for each interpolator. All right, so it's important to note that the semantics here refer to specific UV channels. The semantics here is just a way to tell you that this is a different one. It's kind of boilerplate. I kind of wish you didn't have to define all of these text chord because it feels unnecessary, but anyway. For a very basic shader, we might just pass a single UV coordinates, and then we might as well name this variable UV, right? Let's see, why do we call these interpolators? So let's say I have a mesh. We're going to look at this side on right now, right? We have a vertex and we have a triangle. In this case, it's just a line. And we have some data in these things, right? So that data could be a normal direction, right? It could be the direction that this is facing. And the normal, like I mentioned before, is part of the vertex. There's no normal data here. So the next vertex has a normal here, next one has a normal here, and the last one has a normal here. Actually, let's make this a little bit more clear. Okay, so now we might get a normal like that. This one is going to be like the same direction, which is a little confusing, but that's okay. Okay, so now what's going to happen is that the vertex shader, again, it's a for each loop over every vertex. And then we pass data to the fragment shader, where we're going to render for each pixel. And then you might ask yourself, well, the pixels are not just on the vertices. You're going to have a pixel that's going to render in the middle of this, right? It's going to be on like a triangle face somewhere. So then if we pass the normal to the fragment shader from the vertex shader, the way that that data is going to look in the fragment shader is that it's going to be interpolated, as in it's going to be a blend between this normal and this normal. So the interpolated data in this case means that it's going to be, the normal is going to like smoothly blend over to point more and more in this direction, right? And going this direction, it's going to start tilting down into pointing in this direction. And this goes for any data. So let's say you have vertex colors. Let's say you have the color red there, and then you have the color blue here. So if you then get the vertex colors and you pass that to the fragment shader, the color you're going to get at this location is going to be a blend between these two. Because again, it's interpolating or lerping, if you want to use that, between these two states. So what you're going to get is sort of a smooth blend like this, right? So then you're going to end up with sort of the halfway color of those. That's why they are called interpolators sometimes, because any data that you set in the vertex shader that is going to be passed to the fragment shader is going to be interpolated exactly in that way, whatever data that might be, right? So in the fragment shader, you don't actually have access to individual vertices or anything like that. All you have is the interpolated data for any given fragment that you're rendering. And obviously there's going to be more. It's not just a single pixel in the center. There's going to be a lot of pixels all across. And like for the 3D analogy, it would be exactly the same thing. If we look at a triangle like this, there you go. And let's say we define vertex colors for this one too. So we have red, we have blue, and we have green. So now let's say we want to draw, like, we want to know what color this one is going to be. So let's say we make a shader that all the shader does is that it outputs the vertex color. So let's say we have vertex colors in the mesh, and in the fragment shader, we just say return vertex color. And that vertex color was something we passed from the fragment shader. The way that triangle is going to look is that it's going to blend these colors together. And it's going to look, you know, something like this. And this is the classic GL triangle. If you have like that one friend that is writing their own game engine for some reason, they're going to be like, oh, look, I made a triangle, right? And the reason it's blending between these different colors is because you supplied some color data in each of these corners of the triangle, and the fragment shader blends that data. So that's the blending you're seeing in the center. If you want to get technical, what this is called when you're blending between three different points like this, it's called barycentric interpolation. But it's basically just a lerp, but for 3 points in like 2D space. But you don't have to do this yourself. This is something that it's going to do on its own, right? So this happens whether you like it or not. It's going to interpolate all the data you have. Sometimes you don't want it to do that. So yeah. Let's see, there was a question. I feel like I missed a step where vertex data was passed into mesh data. Stuck thinking that OpenGL redefined a vertex array object for the vertex data layout. You don't pass vertex data into mesh data. That happens automatically by Unity. So Unity is passing all the data into the mesh data struct. So you don't need to deal with that. So this is like automatically filled out by Unity. Okay, so now we've just talked about like what interpolators are. We haven't actually looked at the vertex shader. And here we got the actual vertex shader. All right, so this is a function, just like any other function. It has some input parameters. It has the mesh data, right? So the mesh data is coming in here. So that's the struct. So if we want to access the normals of this mesh or the UV coordinates, we can do that using the V variable, because that one is already populated with data. We're going to ignore fog, so I'm just deleting everything fog related. We're going to ignore textures as well. And the vertex shader, all it returns is these interpolators, right? And interpolators is like data you specify per vertex. So what you specify in interpolators is what data do we want to interpolate across all of these, across this whole surface, right? Because again, all the data that each fragment shader has access to is the interpolated version of this. So when you're in the fragment shader, the only color you have for this fragment is going to be the color that you get here, right? The fragment has no idea what color this is, what color this is, and what color this is, right? Yeah, so that's why you can sometimes call them interpolators, because you get the interpolated value of whatever it is you define in the vertex shader. Okay, this is the vertex shader right now. All we're doing is we get mesh data, and then we set the vertex interpolator. This is the specialized one that always has the clip space position. So Unity has a built-in function called the Unity object to clip position. If you want to get technical, this is multiplying by the MVP matrix, which is the model view projection matrix. But essentially what it does is that it converts local space to its local space to clip space. That's all it does. And then it sends that to the interpolator called vertex, right? And usually O is used for the output if you want, like, if you want to know why it's called O. Right. So that's it. That's all we're doing right now. We can wait with UV coordinates for now, actually. Let's not do UV coordinates. Okay, fixed for. What is fixed for? What is happening? What is this? All right, so you're probably familiar with float for. In Unity C#, this would be the same thing as vector for, right? And the same thing goes with like float 3, float 2, and floats. But in shaders, you have some extra data types that are lower precision than floating point precision. So this is a 32-bit float. But in shaders, you also have fixed and half. So you can say, let's just do float. So float is a 32-bit float. Half is a 16-bit float. And then you have another one called fixed, which is a little weird. It's kind of like, it's very legacy at this point, and almost no platforms you're ever going to target has the fixed precision. But it's very, very low precision. I think it's around 12 or something weird like that. And I think it also depends on the platform. So sometimes it's not just 12. Anyway, lower precision. There we go. And the fixed one is pretty much only useful within the like -1 to 1 range. Outside of that, you get so terrible precision that it's not going to be useful, right? Half is pretty good for most things. You very rarely need to use float, actually. But half precision, you can get away with a lot of things, as long as you do them in the correct space. Float works well for anything in like world space and stuff like that. But half is usually the one you're going to use. But when you're doing things in practice, you can just use float everywhere. And some platforms don't even support half and fixed. I think some like PC platforms never use half or fixed. They always have everything in floats. But if you're doing things on mobile, then half precision is going to be important. And then there are some other variable names that might be useful. So again, you can do this with vectors too. So while there's a float for, there's also a half for, there's also a fixed for. So this would be the vector for version of that. And they continue with this like naming convention. So if you want to make a matrix, then that's called float 4 by 4. And again, you can do half 4 by 4 for a half precision 4 by 4 matrix, and so forth. Yeah, so this is how you do matrices, where this in C#, the equivalent would be matrix 4 by 4, right? And you can do like 3 by 3, 3 by 4 matrices as well. There are some data types. Bool data types kind of exist, but generally they're equivalent to values of 0 and 1, which is familiar to some of you, because I'm sure some of you have used, you know, C or whatever, where I think bool is like equivalent to a 0 and a 1, where you can just multiply by a bool. So yeah, so you can like multiply something by a Boolean value, and that's going to compile, and false would be equivalent to a 0, true is equivalent to a 1. You can have integer values as well, but in many cases, it's just going to be converted to a floating point value anyway. But usually you can have int values if you want to. Yeah, but generally where you're going to be using like 99% of the time is just floats everywhere, because it's not going to matter for a very long time unless you'd like start optimizing things specifically. Oh, and then a fun thing is that this vector format kind of translates to everything else. So you can use an int2. You can probably do a bool 4. Yeah, it's shaders. So you can just add a number for how many components you want in that thing. I think. I actually never use these, so I don't know if it's possible, but I'm pretty sure it is. Okay, what's the value of doing lower precision? Does it use less RAM or is it faster? It is generally faster. And in some cases it uses less memory as well, depending on what you're doing. So if you're doing things like GPU instancing, then the number of bits that your properties can take, or the number of bits that they occupy, kind of determines how many instances you can have in a single rendering batch. Not to get into too much into instancing and what that is, but yeah, generally on like lower end platforms, you want to use lower precision stuff because the calculation runs faster. You don't have to do a full 32-bit flip. And then now we're in the fragment shader. We're going to delete fog and we're going to delete textures. Should you always use lower precision if you can? Pretty much, yeah. That would be a good rule of thumb. I would generally caution you to not care about it until you have to, because you can run into some really weird and hard to debug issues when you're using like too low of a precision for something. So the way I approach it is use float everywhere until you have to optimize, or unless you like really know what you're doing and you're not experimenting anymore, right? Cool. So now we have our actual fragment shader. So the fragment shader has a semantic here. This semantic is just telling us that this fragment shader should output to the frame buffer in most cases. That should be the target of this fragment shader. In some cases, if you're doing deferred rendering, you can write to multiple targets, but we're not doing that in this case. It's just a single target. So then we just use the semantic sv_target. Again, it's mostly boilerplate. This is always there, basically. So now we have basically one of the most simple skeletons of a shader. You don't usually modify that much apart from adding code inside of the vertex shader and the fragment shader. Although sometimes the render pipeline tags and the properties, of course, you need to modify. Okay, so let's do the hello world of shaders. Let's output a color. So let's do that. Let's output a float 4, and let's give it a nice color. Give it a red. There we go. Oh geez, I don't want to auto format. All right, so this is just a red color. And like I mentioned before, in the math class we had, a very good rule of thumb to remember is that RGBA directly corresponds usually to stuff like, you know, X, Y, Z, and W. So these would be the components of a vector, right? Like the X component and the Y component, Z component, and so forth. But for colors, this would be RGBA, right? And of course, you can also index them. You can call this 0, and this is 1, and this is 2, and this is 3. Shaders make no distinction between colors and vectors. They're all the same. All of them are float 3, or they're float 4 or float 2 or whatever. So everything you do in shaders is pretty much always structured this way. So there's no color type in shaders, and there's no vector type. It's all the same, right? Because they have exactly the same structure, you have a floating point or some other precision value in up to 4 components. Oh, what is A in RGBA? So A is usually called the alpha channel. Alpha channel can be used for many different things, but the most common use case for the alpha channel is used to represent transparency or coverage. So you can use it as a transparency thing, or you can use it just to pass some other data along, right? The same way that sometimes with vectors, you also use a W component just to pass some data, which is more common than having a 4-dimensional vectors. All right, so now we got the fragment shader. We're just returning a new float 4 that's just red. All right, so let's try this shader. Let's see if it works. Let's see, output value vert not completely initialized. Okay, so it's complaining because I have not set the value of the UV interpolator, so I'm just going to comment that out. There we go. All right, so we got our first shader, but we need a material. We can't apply a shader to an object. So even though we might have an object, we can't just drag and drop the shader onto that object. We need to have a material to define what are the properties going to be for this object. So I'm just going to create a material. There we go, and this is now using our shader. And then we can apply that to our object. Yeah, and there you go. This is our shader. We made a shader. It does indeed output red. Something I love about shaders is that we can do, Swizzling, yeah. So Swizzling is a funny name for a pretty basic, but very useful thing of like, if you have a float for my value, then you can access these components or cast them to a vector2 by doing myValue.xy, and then that would be a float 2 like this, which is pretty useful. So this is like you can just cast it to a vector2, and you can replace x and y with r and g for red and green. So you can use whatever components you want to use from this set, right? Or not the numbers, so these letters. And you can even flip them. So you can do myValue.gr, and it's going to flip the, it's going to assign the green channel to the red channel and the red channel to the green channel. So this is called Swizzling, and it's incredibly useful. And sometimes if you just want to output a grayscale of some color, you can do .xxxx. And now this is going to just take the first component and then splatter it out on all the 4 components of something. Super useful to have. And yes, it is frustrating to not have that with Unity's vector type. So we made a color, right? We output a red color. So what can we do with this? Well, we can make it output green if we want, right? So we recompile and now it's green. Can you do RRR1 to automatically put 1 in the alpha channel? No, but this is something that I am pushing hard for. I really, really want this to happen. And my girlfriend, Ashley, is working on, she's working on Rust GPU, which is basically like a way to write shader code in Rust. And I'm trying to get her to push for that change. There's some discussion about this on the internet as well, but it gets complicated because if you want the first component to be 0, then that gets complicated to compile because doing .0 is not a valid variable name or a field name, right? But yeah, anyway, all right, so now we have a way of outputting a color to the screen. And we can move this around, and it's following the transform of this object, which is like, seems like it's a very basic thing, but the reason this happens is because we told it to convert local space to clip space here. So this is not always the case. So the default space is the clip space, right? So if we just set this to v.vertex, it's going to be like stuck to the camera. It might not even render. No, wait. Okay, we got it. So now we just took this mesh, but we're rendering it directly in clip space. So now the position of this object doesn't matter whatsoever because we're not using that matrix, right? Now it's just like slapped onto the screen. So this can be useful if we're doing stuff like post-processing shaders, because for post-processing shaders, you usually want to have something that covers the entire screen, right? It doesn't have a position. It's just a global thing for the frame, right? Okay. Oh, the difference between like normalized device coordinates and clip space. It seems really messy, and it's really hard to find good information on that. It just seems like it's mostly a difference in like axis orientation and whether or not depth should go from 0 to 1 or -1 to 1. Whereas in clip space, I feel like depth goes further, but in normalized device coordinates, it's squished into either 0 to 1 or -1 to 1, right? You don't have to know that in order to write shaders though, which is kind of nice. At least you're writing your own engine, but that's not why we're here. How compatible are the shaders you write in ShaderLab, OpenGL, Vulkan, DirectX? Unity cross ports to all sorts of render, I don't even know what to call them, render APIs. So like if you compile something for iOS, it's going to compile to iOS Metal, right? So like the actual backend is, you don't have to care about that. You only write stuff in HLSL, and then Unity is going to handle all the like translation to all the different APIs. Is it all compiled to SPIR-V nowadays? I don't know. I would guess not, but maybe. You can probably look it up. I don't really know how the internals work there. Like I quite often mention, I pretty much only learn the things I have to learn. So if there's information that's mostly useless to me, I tend to not pick it up. So for me, to make things look pretty in a game and to code the shaders that I want, I don't need to know that. I just need to know that it compiles for the target platform. Can you have multiple shaders on one object for different purposes? Say I want an outline shader when I hover over the objects, but I also want to have another shader on them at the same time. Usually you can like do stuff like you render the mesh twice with different shaders. Yes, you can do that. Outlines in particular are like notoriously complicated. So sometimes outlines are even done as a post-process effect rather than, you know, something that's in the shader of the surface itself. So it kind of depends on what you're doing. Rust GPU looks like it uses SPIR-V. I'm pretty sure, yes. Actually, Rust GPU uses SPIR-V, right? Thumbs up, yes. Is it possible to replace VFX with shaders for non-art background? So you can't like, well, it depends on what you mean by VFX and what you mean by shaders. Because all the VFX that you use and draw do use shaders. Shaders are kind of inevitable. Everything that you can see in a game is pretty much always rendered with shaders. But if you're asking like, can I replace like artist-authored texture data with shaders? Sometimes, but sometimes it's also like pretty like computationally expensive to do that in real time when you can just use a texture that someone has like authored. And usually it's like, it's also a different style, and it really depends on what you're trying to like artistically achieve and what your like capabilities as a team are. So let's continue. So we made a very simple shader with a hard-coded color. All we do here is we have a fragment shader that is positioning the vertices at some position in the world, right? In this case, it corresponds to the transform of this object. And the fragment shader, the only thing it does is that it returns a green color. That's it. So let's do something that's a little bit more useful and interesting. So first off, let's make a property, because maybe we want separate materials for this. Maybe we want one that's green and another one that is red. Let's say that we want to have a green one and a red one, and we want to be able to configure this. Okay. We want to have a property for the color of this. So this is a float property, but in our case, we want a color, right? So let's call it color and give it a name of color. And we just call it a color. Color. And a color has 4 components. So we can default it to some value. Let's default to, actually, can probably just do 1. There we go, 1 across the board, white color. And then we want to be able to access this property somewhere, right? The properties that you define here, usually you need to define a variable for that too, or a field for that. And again, colors are have 4 components, so you can either do float for, fixed for, half for, but we're just going to do floats. And so now we have the color property, and we can set this color property in the different materials that we have. So then we can access this both in the vertex shader and the fragment shader. We can access the properties from anywhere, which is really, really useful. So in this case, instead of outputting a hard-coded color value, we're just going to output _color. Save that, go back to Unity. And so now if we select the, let's see, this is the supposedly red one. Let's copy that and assign the green one. So if you now look at the material of this, we now have a color property on this material. So we can then modify this color. So this was the green one. So let's set it to green color. And then we have the red one. So let's set that to a red color. There we go. So now we have a green one and a red one. And we can now configure this per material because we have this property up here, right? So this property has a field called color, and we can then access that field in the fragment shader, which again, the fragment shader, all it does is return a color for the current fragment or sometimes pixel that we want to render. But so far, we haven't actually passed any data from the vertex shader to the fragment shader. All we're doing is just like shitting out a color, right? Or I guess that's what you always do in a fragment shader. But in this case, we want to get a little fancier. So what if we want to pass something from the vertex shader to the fragment shader? Okay, so let's talk about the concept of UV coordinates. So now we're going to get into what UVs are. Oh, actually, we're not going to do UVs. We're going to do normals. We're going to skip UVs. All right, so in order to pass something from the vertex shader to the fragment shader, we need to pass that in the interpolator structure, right? And we need to have a float3 value because normals are, it's a three-dimensional vector, it's a direction. So let's call that normal. And then the semantic we use for that, we just call it text coord 0. It doesn't matter. This does not correspond to UV coordinates in the interpolator structure. This corresponds to just one of the data streams that we have coming from the vertex shader to the fragment shader. And all right, so now we got the normal in the interpolators. And we can access that because we have the interpolator's input in the fragment shader. So we could do I.normal, and now we're going to access whatever we set the interpolator to here, right? Now I.normal is a float3, but the fragment shader is going to return a float4. So we need to specify what's the fourth component going to be. Well, we can do float4, and then we pass I.normal in, and that's automatically going to populate the XYZ components, and then we're just going to set the W components to 1. Because usually in this case, that's usually alpha if you're using alpha blending or like transparency. But in this case, I guess it doesn't matter. We could just make this a float3, but whatever. Yeah, so in this case, it's just making a float4 out of a normal direction, which is 3 components, and we're adding another component to that. Okay. So now we are outputting the value that we have in the interpolators, but we haven't set that value yet. The vertex shader needs to assign something to the interpolator called normal, right? So in this case, we would do O.normal equals, and then we give this some value. And again, like I mentioned before, this can be anything. It doesn't have to be normal. We can even pass the color in here. Let's say we pass the color.rgb into O.normal. Then if we go back to Unity, we're still just looking at the color now. But instead of directly outputting color here, we're passing it through an interpolator. So all we're doing here is just piping data to the fragment shader. But we don't want the color. We want to show the normals of this object. Just visualize the normal directions, right? The way we can do that is that we need to access the mesh data, right? Because the mesh data contains the normals. Because again, mesh data has the normal here, and we use a normal semantic to make sure that it populates the normals variable with the normals of the mesh. So if we now go back here, we can do O.normal equals V.normal. And this is very common. You will very often just pass data through the vertex shader immediately to the fragment shader. So this one is not actually doing any transformation and whatnot, but we should, and we're going to get to that later. All right, so we're passing the normals from the mesh data to the interpolator that we're going to have across all the triangles. That's going to get passed to the fragment shader. So now we can access the normal. So now if we go back to Unity, we have these very colorful mango spheres. So now what this one is showing is that it's displaying the direction of the normal for every given pixel that we are rendering. And a way to sort of visualize this is that if you consider what normals are, it's the direction out from the surface, right? And again, like I mentioned before, shaders make no distinction between vectors and colors. So what we're doing now is we're basically outputting the vectors as a color. So on top of this mesh, it's green, right? And what that means in a vector is that we have the values 0, 1, 0, because in the center component we have the y component, and that one is 1, which means it's pointing directly upwards, right? So that's why it's green on the top. On the x-axis, the normal is pointing directly along x, and that's why it's red. On the z-axis, it's pointing along z, and that's why it's blue. So what this is doing is that it's basically just showing the direction of the normal. Why is normal semantic in interpolators? Text chord, wait, S? It's text chord 0 in this case. So text chord, this is kind of just a name to specify a slot of where you want to pass data through. So like I mentioned, in mesh data, text chord specifically refers to UV coordinates, but in the interpolators, text chord is just an index. You don't really need to think of it as anything related to anything when it comes to mesh data. So in this case, text chord is something completely different. It's just the semantic you use in order to separate all the different values you have. So if you want to add something more, you name the next one text chord 1, name the next one text chord 2, and so forth. And this could be anything. This could be the tangent. This could be just some values. It could be whatever you want, right? So this is just a way of saying that you want to have some channel where you pass some data into it, right? I'm seeing the black side render correctly. Does that mean you can have negative color values output by the fragment shader and nothing will break? Yes. Shaders are like inside of the vertex shader and the fragment shader, they're kind of designed to never crash. So if it compiles, it will output something. The downside of this is that you can literally divide by 0, and you can get NaN propagation throughout your rendering pipeline, unless you're careful, because shaders will not like crash for that reason. But it kind of depends on what you're rendering to. But yes, you can render, you can have negative color outputs. You can have values above 1. It's not restricted to 0 to 1. And depending on what you're outputting it to, it has different effects. It is possible to render to a texture. And it's also possible to render to the frame buffer. In this case, we're rendering to the frame buffer, but you can render to like a floating point texture if you want to. In which case values below 0 are going to stay values below 0. What does NAND display as? I don't remember. I don't quite often run into that. And there are sometimes there are protections against that to prevent NAND propagations as well. I think the newer render pipelines in Unity has protection for that. Okay, cool. So we're just passing the normals through. All right. So now we're basically showing the normals of this object in color. And this applies to any object. So we can replace this mesh. It doesn't matter what mesh we're using, right? So we can just use a capsule or a cylinder, and everything behaves as we would expect it to, right? So that is the normals. All right, let's look at something else. Oh, actually, one more thing. So if we rotate these, you can see that the normal that we're outputting is not in world space, right? Because you can see that this corresponds to the local space axes, or in this case, it's sometimes called model space or mesh space. So these normals are not converted to world space, and we might want to do that. So this is where we can start figuring out, where do we want to do this math? Because technically, we could do that either in the vertex shader or in the fragment shader. If we want to do that, we would do Unity, is it model or local? Probably local. Objects to world normal. There we go. Object space is what Unity calls it. So this is a Unity macro that basically just converts this from object space to world space, right? It's called normal because this macro does some extra stuff depending on how you configure Unity. So there are lots of shenanigans that happen if you scale your object with non-uniform scaling, because then you want to make sure that the normal is normalized. So there are all sorts of things you might be careful with, depending on how your object is set up. But if you don't have any scaling, then it's pretty much just a matrix multiplication, right? As you can see here, it's a mul, which is multiply with matrices. So it multiplies a normal vector with a 3x3 matrix of world to object, right? And yes, this is from Unity's include file. And you can do this manually if you want to. So if you want to do this manually, you would do mul, and then v.normals, and then the matrix here. Which one did they use? This one. There we go. So unity world to object is a 4x4 matrix. But if you're doing matrix multiplication of a direction, you can just discard the fourth column in a row, right? Yeah, right. And this is a little confusing because it says world to object, but what we're actually doing is object to world. But the reason for this is that the parameter order of the multiply operation changes the matrix. The matrix will either be transposed or not. So if you want to make this a little bit more readable, which I would do, I would never structure it that way. I would instead use unity object to world and then flip the arguments. So now it's a straightforward multiplication of a 3x3 matrix with the object space normal, and then we transform it to world space, right? Yeah, and we don't use any scaling, so we don't need to normalize this, so we can just leave it as is. Oh, you could also use the unity matrix M. This is the model matrix. So if you've heard about the MVP matrix, the model view projection matrix, this would be equivalent to the unity object to world. Unity themselves recommend using their names because they usually define like those names to work in different ways depending on like platforms. It gets really complicated once you get into VR and stuff like that. So usually it's best to use Unity's built-in stuff for this. But yeah, I just wanted to show you how you could do space transformation manually. So now this is no longer in local space. So if we rotate this and then recompile, the green is going to change direction, right? So now no matter how we rotate this, it's always going to correspond to world space normals, right? Because we transformed those vectors. And the same thing goes with this one. You can see that this one is going to change to green. We can change it to red, and we can change it to blue. Whew. All right. So we could, if we want to, we could do this in the fragment shader. We could pass the local space normals here. And then we do this operation in here, right? So if we recompile, nothing changes. It works exactly the same way it does before. But this is where one of the most common ways to optimize shaders comes in. So if you want to think about how you can make a shader faster, try to think about how many vertices do you have versus how many pixels or fragments do you have? And in most cases, not all, but in most cases, you have more pixels than you have vertices. So you usually want to do as much as possible in the vertex shader and do as little as possible in the fragment shader. It could be the case that you have some really like high vertex count on something that is very far away, in which case it might not have like, maybe it's only rendering to like 32 pixels, but it has like 16,000 vertices. In that case, it's going to be more expensive in the vertex shader, right? But in most cases, you're going to be running more pixels than vertices in a mesh. So usually something like this, if you can put it in the vertex shader, then you should put it in the vertex shader. Presuming you didn't need access to the like local space normals in the fragment shader. All right, so normals is just one type of data that we have in our mesh. So let's move on to UV coordinates. So we have the UV channel 0 as our mesh data input. And then in the interpolators, we want to send the interpolated UV values to the fragment shader. So we need a channel to do that on. So we're just going to call this UV. So now we have UV. And then in the vertex shader, we do O.UV equals V.UV0. All right, so this is, again, just a simple pass-through. We're not modifying this at all here. Okay, so what do the UV channels look like? Let's just output the UV channels. So I.UV01. Because UV channels are, or UV coordinates, if you're using the traditional UV coordinates that you have like in your mesh editing programs, usually UV coordinates are 2D coordinates, right? So in this case, it's a 2D vector that we pass into the float4. So then it combines it into a full float4 where Z is 0 and W is 1. So what does this look like? Well, we get even more mango shapes. So the UV coordinates depends on how the object was UV mapped when the artist authored this object, right? And it's probably most helpful to look at the way that it looks on a single quad. So here we have a single quad. So what UVs are, if you think about the colors that we're seeing here, they directly correspond to two-dimensional coordinates, right? Because colors are vectors and vectors are colors in shaders. This is a very useful way to debug this. So the vector, or the UV coordinates, or the color, is 0 in the bottom left corner, because it's fully black. And along the bottom side, you can see that it's increasing in red, and red is the same thing as the x component. So the x coordinate is increasing along here, but on the other axis, it's increasing along green, which is the y coordinate. And then diagonally, it's increasing across both, which would make for a yellow color. So what we're visualizing is 2D coordinates on this mesh. And if we want to visualize just one of the components, we can do i.uv.xxx, for instance. So now we take the x component and splat it out across RGB. And now we just see the x component of the UV coordinates, which just makes for a horizontal gradient, right? And we can do the same thing for the y coordinates. And now we get the y coordinate there. It's just that when we visualize both at the same time, we tend to get this mango vibe going. Because it's just red and green being added together in a single color. So this is the coordinates that you get in a 3D application when you are modeling something. So if you have a cube like this, then depending on what face it is, the colors would be different depending on where it is, right? Because that's literally what the UV coordinates are. They specify a 2D coordinate on your mesh. Yeah, not always, but usually. Here's a good thing to talk about. So let's say we want to modify this with a property. Let's say we want to scale these. Let's say we call it UV scale, and that's going to be a single float value, and it's going to start with 1. That's a good default for a scale. And then we need a variable for that, so we're just going to call it scale. And now we want to scale these UVs based on this parameter, right? So if we then want to scale this, then we can kind of consider, like, what does scaling mean? What we kind of want to do is that we want to multiply these vectors so that they get either longer or shorter, right? And you know vector math at this point. So if you multiply by scale, the coordinates themselves will change depending on what this value is. And again, we can do this in the Fragment shader as well, but since it's faster to do it in the Vertex shader, we're just going to do that in the Vertex shader. So now we scale these UVs with some value. So if we now go back to Unity, what happens if we tweak this value now is that you can see that the coordinates themselves change. If we put the scale to 2, for instance, you can see that it's maxed out at yellow here. And then this quadrant is just completely yellow because all of those values have gone above 1, right? So the color is clamped, but the underlying data is not. You still have values outside of 0 to 1, but visually your monitor can't show negative colors, and your monitor can't show colors above 1. So that's kind of the range that we can see stuff in. But you can still use those values in the shader itself, right? So this is how you can very easily modify data like this. And the part that I really love about working with shaders is that it's kind of fascinating how closely you can visualize math and like things you would do in math. So in this case, we multiplied by scale. So what if we do some other stuff? Let's say we have something called an offset. Let's call that offset. Default is 0. The additive identity. There we go. All right, so if we have a scale and an offset, then usually offsetting would be that you add instead of multiply. Whether or not you want to offset before or after scaling, I guess depends on your use case. But in this case, we're going to do it before. Actually, do you want to do it after? I don't know. Things always feel a little reversed. All right, so now we have an offset parameter. So let's set the scale to 1. So now we can offset these UVs diagonally, right? we can put a negative value there and we start moving the coordinates to be negative, or positive values, and they're all like positive, right? And this is where things start becoming really, really powerful. Because if you start thinking about how maybe we want to, fade something from one color to another over some specific range, this is where we can start doing stuff like that. So let's say, for instance, that we want to make a gradient from one color to another over the UV coordinates. Let's say that that's our goal. All right, so what are we going to need? We can start out by having the two colors, right? We have color A and color B. So that's going to be our start and end colors. And let's say that we just want to do this across the x-axis. So let's ignore scale and offset for now, just pass the UV coordinates through. Now, we want to blend between two colors. Oh, we also need the properties here. Color A, color B. Don't use these anymore. All right, so you probably remember that we talked a lot about the function called lerp, right? And lerp is basically a way to blend between two values based on a third value, usually between 0 to 1, right? And if we think about the UV x coordinate, then this is a value from 0 to 1, right? 0 on the left side, it's 1 on the right side. So we can use this as the t parameter of a lerp function between two colors. So let's say we want to make a variable. Let's call that our output color. And we're going to lerp, and in shader code, you just type lerp. The from value is going to be color A, the to value is going to be color B, and the interpolator is going to be the x coordinate of the UVs, right? And then we can output that color. Okay, so this is basically blend between two colors based on the x UV coordinate. All right, and we're back in Unity. And now we can set this to some color, and we can set this to some other color, right? So now we've done a very, very simple blend between two colors, and we constructed a gradient with very few instructions, right? It's a simple lerp between two colors, and all it's based on is the UV coordinates of this object. And then we can start modifying this however we want. Let's say we want to be able to change where the gradient starts and ends. Maybe that could be a useful parameter to tweak. Well, in that case, it might be useful to have two ranges, for instance. So let's call it color start, color end. There we go. And in this case, let's use a range instead. So range is just a quick way to tell Unity that we want the inspector to have a slider between these two values. In this case, it's just going to be 0 to 1. All right, so we have color start, color end. We want to start at 0 and end at 1 by default. And then we want to add these as properties. So as with the other ones, it's just going to be float for all of these things, right? So it's float for. Or no, actually, these are not float for, sorry. Since these are just a single value, we just have color start and color end as single values. All right. Cool. So what we then want to do is that we want to change, or we want to remap the x coordinate of the UVs to some other range, right? So for now, let's stop looking at colors and let's go back to looking at the actual values we want to use as a t parameter. And this is really, really, really useful because in shaders, you can't really log things. So in shaders, you usually want to usually just want to output some color. And that is the way that you can see what is happening in your shader. So if you're writing shaders, you're going to have a lot of commented out lines that just say return some stuff because it's really useful to debug stuff that way. So in this case, we want to see i.uv.x. So this is the x coordinate that we're dealing with. So now we want to make these two sliders change where this gradient starts and where this gradient ends, right? Okay, so we've talked about this during the math class, and a very, very useful function that you can use to do this is called inverse lerp. Surprisingly and oddly enough, inverse lerp is generally not built into shader languages. There is almost an inverse lerp called smooth step, but that one also has smoothing, and it's kind of, I don't know, it's different, right? So sometimes you have to define your own functions, so let's just define our own function. So let's call this inverse lerp. We have a start value, we have an end value, and we have the input value, right? So we got inverse lerp, and the inverse lerp function is really, really straightforward in case you don't care about divisions by 0. In which case you just do return, let's see, it's v minus a divided by b minus a. I'm pretty sure that's the one. So now we have an inverse lerp function, and now we can use this to change where this gradient starts and ends, right? So, all right, let's call this value the t value, because that's usually what it's called in the third parameter of the lerp function. So we're going to do inverse lerp, color start, and color end. And then we're going to have the actual UV coordinates. So that's a gradient input. So then we get the t value, and let's just return that t value for now. All right, let's see if this works. So if we pull the start position, it seems to actually change the start. And if we pull the end of the gradient, that also changes the endpoint. You can also reverse this. The inverse lerp doesn't really care what order this goes in. But yeah, so this is now a very simple thing where you can just change where this gradient goes, right? All right, and then we want to make this be between two colors and not just black and white, but all the data is pretty much there, right? You might think that all you need to do is just bring this back and change this to t. There's one more thing we need to do. Oh, sorry. I still need to return it. All right. So now we're using the t value that we were just looking at, this value from 0 to 1. And we're using that as the t parameter of the lerp between color A and color B. So now if we go back to Unity, recompile, we now have a blend between two colors. Kinda. It looks like we have more than just two colors here, right? And if you can guess why that is, well, how could this happen? Why is there yellow? Does anyone have any idea? And then I'm like gonna awkwardly sit and hell yeah, you got it. So basically the problem is that because shaders don't natively clamp everything between 0 and 1, you need to make sure that you do that wherever you want to keep things within that range. So what's actually happening is that the t value here of the inverse lerp actually has values outside of 0 to 1. So even though we might return t, then we can't tell if these values are above or if they are above 1 or if these are below 0. There are ways of there are ways of checking this. So one way that I like to use for checking whether or not something is overshooting is that I usually like using a function called frac. So frac is a very simple function that basically frac is the same thing as doing some value and then subtract floor of that value. And in the human language, what that means is that values are going to repeat within the 0 to 1 interval. So what would happen is that if we have values that go above 1 here, we would see this gradient repeat multiple times in both directions, right? But if this is clamped, then we wouldn't see a repeating pattern because then all of these are the same values. All right, so let's use frac in this case. Let's do t equals frac of t. And then let's go back to Unity, and we can see that they do indeed repeat, right? So yeah, and we don't want that. We want to clamp this between 0 to 1 and not repeat the pattern. You could if you want to, but that's not what we're going for now. So we are not confirmed that this one is not clamped, but let's clamp this and see what happens. So we have a frac, and then the way that you clamp things in shaders is quite possibly the worst name of a function ever to exist in the universe. The way that you clamp is that you use saturate, which is a shit name for what this is doing. So saturate basically means if it's less than 1, make it 0, or if it's less than 0, make it 0. If it's greater than 1, make it 1. It's the same as the clamp 01 function in Unity, in Unity C#. But yeah, so that's what saturate is doing. It just clamps it between that range. So if we go back to Unity now, we can now see that it has clamped. This pattern is not repeating below or above it, right? Because we clamp it and then we do the frac operator, which would show us repeating gradients in case it was still increasing here or if it was still decreasing here. So good. That means that we have now successfully clamped this, and now we know that these values are stuck at 1, these values are stuck at 0. So now if we go back to the gradient, we'll now have a single gradient here, and it doesn't overshoot into other colors. This might be a topic for later, in which case don't answer. Oh, I don't know, I haven't read it yet. What's the difference between what we're doing now plus a clamp and smooth step? So smooth step is a little different because smooth step is an inverse lerp. It's a clamp and a cubic function. So smooth step has like 3 different things that have a bunch of operators that you might not always want to use. So smooth step is, yeah, it's a combination of those three things. Yes, it's not a lerp, it's a cubic smooth, which in and of itself can be useful, but yeah. Oh, for context, the reason I think saturate is one of the shittiest names for a function is because like you're literally dealing with colors in shaders, and saturate means something completely different in the context of art and colors, which is really frustrating to me. Did that make sense? Any questions so far? Is saturate also part of Unity's include? Nope. Saturate is a built-in function in the language itself. Usually the page I go to is the CG deprecated documentation. Here you go. The standard library in CG lists a bunch of functions. So if we go here and we search for frac, you can see that we have frac, and you got all the different overloads for all the different precisions and the input values and whatnot. Oh, it's also really useful. It does also show you, if you were to implement it manually, this is how you would do it. So, which is, yeah, that's the thing I was just mentioning, which is funny because then we can look at smooth step and you can see that smooth step is doing a hell of a lot more than just an inverse lerp, right? So if we look at smooth step, this is a linear inverse lerp. And then it's clamping it between 0 to 1. So this is the part that we were doing manually. And then it's doing a cubic smoothing of that function. So it has like a lot of extra math that you don't always want whenever you're doing this. So just to show you what that looks like. There you go. So this is the cubic smoothing function, whereas the one we were doing is the green line here, where it's just going to, it's just a linear blend, whereas smooth step is doing the smoothing curve on top of that. I guess this should just be between 0 and 1. Yeah, so that's what smooth step is doing. Isn't saturation basically RGB times X? It's not RGB times X. Like if you do that, you multiply it by a value, and that would still make it shoot beyond 0 to 1, right? If you're talking about the artistic saturation, just multiplying is not going to change the saturation of it. It's going to change the overall brightness, but it's not going to change the saturation, which is sort of a separate thing. If you want to increase the saturation of something, you first need to figure out what is the grayscale value of this, and then do the opposite of that. So usually something you can do is you can interpolate away from the grayscale version of that color, which is like a sort of separate operation from the thing that shaders call saturate, which is just a clamp between 0 and 1, which again, it sucks that it's called saturate. It should just be called clamp 01 or whatever. In that case, the shader saturation makes no goddamn sense. No, that's why I hate the name of it. It should be called clamp 01, but that's why it's called clamp 01 in ShaderForge. Literally, yes, that is why it's called that. Let's see. We don't have that much time left, so I can just juggle a few math things to show you what you can do with this type of stuff. Let's give it some more pleasing colors. I didn't like these colors. This is better. I like this better. Okay, so one thing that is really neat is that So let's say you have your, actually let's keep this for later. Oh, that's not necessary. Oh, by the way, things in shaders automatically cast from a single float to a float 4. So we're returning just a single float, but this is basically going to take the X component and swizzle it out to all 4 channels of the float 4, or the 4 components. So in this case, there's an implicit cast. And so right now we're just showing the basic UV coordinates that we looked at before, just 0 to 1 from left to right. And one thing that's really nice once you get into making shaders this way, and once you can like harness the way that the math functions work, is that you can get a lot of effects out of it that might otherwise be really hard, especially when you get into like animating things and like trying to do procedural stuff. So let's say, for instance, I want to make a triangle wave out of this. Then there are like, you can sort of deploy a bunch of math here and then just sort of make it work. So say we want to make a triangle wave, how can we go about that? Well, we can sort of look at Desmos for range values. So now we have a simple curve from 0 to 1, right? And let's say we want to make a triangle wave out of this. Well, we do have the function abs, right? Which we talked about in the math class, which basically means if it's negative, make it positive. So it's the absolute value of something, right? So given that, we can then sort of start thinking about, okay, so if I want to make a triangle wave that is sort of repeating over some range, what if I take this value, multiply it by 2, subtract 1. Now it's going from -1 to 1 over this interval. And then if we do abs of that value, you can see that it's now bouncing from 1 to 0 to 1. So now we have a triangle wave inside of the 0 to 1 range, right? So now it's just a very simple mathematical function to do this. And obviously we can repeat this. So if we then go back here and we have our coordinates here, and we first multiply it by some value, let's say 5, and then we do frac of that. So if we go back, we now have 5 repeating sections of 0 to 1, right? And then we want to try to turn it into a triangle wave. So then we can do the same thing that we did here, right? Absolute value of x times 2 minus 1. So all right, so we take this, multiply it by 2, subtract 1, and then we take the absolute value of that whole thing. And then if we go back to Unity, we now have a triangle wave. So this one is now going from 0 to 1, and then down to 0 again, and then up to 1 again, and so forth. And you can do this in many different ways. You also have the trigonometric functions, so you don't have to do waves like manually like this. You could also do the, let's say you do the cosine of this value, because as you know, trigonometric functions repeat themselves. So if we do cosine of x, in this case we did times 5, it's not going to repeat that many times because the circle constant is involved. But we can just throw some constant in there, let's say 25, go back to Unity, we'll now have a repeating pattern, although this one is going from -1 to 1, because that's what this one outputs, right? Tau, should we involve tau? Let's do it. Thanks, Joule, for the tau value. All right, define tau, that number. There we go. This is a preprocessor define. It basically makes it so that any instance of this is going to be directly replaced by this. You can define things as like names of stuff, and like you can make macros. You can go kind of crazy with like preprocessor defines. In this case, I'm just going to define that as the constant. Yeah, so now if we do this coordinate times tau and then an integer value, this is guaranteed to repeat perfectly and seamlessly. It's going to start and end on the same value. So this guarantees that we're going to go through an entire period. Yeah, so now if we go back here, starts at 1, goes down to -1, goes back up to 1, and so forth. And this thing of like remapping from -1 to 1 to 0 to 1 or vice versa is something that like I tend to do a lot after a while because it's very common to both like juggle these two ranges. So in this case, I would multiply by 0.5 and add 0.5. So that kind of shifts the range that this is in. So now it's going from 1 to 0 to 1 to 0. Freya's just having fun now. Yes, I had to kill time for 10 minutes before lunch. But I also wanted to show that like as soon as you start like harnessing this type of like math stuff, you can do a lot of like fun things with this. And you can animate this if you want to. It doesn't have to, you don't have to like have static things. You can do it in different spaces. It doesn't have to use UV coordinates and so forth. There's a lot of stuff you can do with this. But I feel like we should explore that after the break. So we're doing a lunch break. All right. So is there anything you would like me to recap or talk about that we've already talked about or clarify something? If so, do let me know. Can we do a quick 1 minute recap? Yeah. Okay, I can try to do a quick one. I tend to make them way too long, but let's do a quick recap of the shader that we wrote at the very least, because I'm guessing that's the one that has this most information dense. All right, so to like recap the structure of a shader, the shader itself is kind of the outermost scope here. This is the path to the shader when you select a shader. I didn't mention that before, but basically, if you have a material, you can select between different shaders. So the path to where the shader lies in this whole group depends on the path you have at the top of your shader. It can sometimes be useful for like categorization and stuff. All right, and then we have the properties. And the properties is basically all the stuff that individual materials can modify and have as input data for this shader. So generally, all the properties, that is stuff that you can tweak with this. Everything else is hard-coded, pretty much. There are some exceptions. There are some things that are populated by Unity. The mesh data is populated by Unity. And so some of the like positional stuff, like the transform matrix, the MVP matrix, like light information is also supplied by Unity automatically. But basically all the custom stuff that you generally want to input to your shader is defined by the properties. All right, then you have the subshader. Most shaders that you're going to write are only ever going to have one subshader, but if you want, you can have several subshaders in a single shader file, which you can then select between depending on like performance characteristics or whatever, using the level of detail thingy. I don't know how that works. I never use it. It's probably not relevant. There you go. And then you got a bunch of tags. So these are the configurations for how you want this subshader to act. There are sometimes also tags here. This is usually called pass tags. And then you have subshader tags. It's important to make a distinction between these because it's easy to get them mixed up where you like try to enter subshader tags and the pass tags. So it's important to like know the difference between the two. But that can easily, you can easily do a Google of like Unity shader pass tags. And if you go here, you can then see, okay, what are the value, like the valid tags that we can have in our pass, and so forth. So you can just Google any of these things and you're going to find it. All right. Is there a way to see all shader paths, including hidden shaders? With the reflection, I think there is, but I don't know if there's a way to do it in Unity, just with the vanilla editor. Will we go over transparent and opaque and the order in which things render and such? Yes. Okay. And then we got the CG program, which is the same thing as HLSL code. So what's within the CG program and end CG scope is code or shader code. Everything outside of that is just called Shader Lab. It's Unity's like wrapper language to encapsulate all the data we need to supply and interact with our shaders. All right, so and then in the paths is where we define our shader code. So in this case, we have a vertex shader, we have a fragment shader, we include some of the Unity like built-in variables and stuff. We define tau because tau is useful. And then we've got our properties defined as variables. And we need this in order to be able to access them. All right, this is a little messy. I don't know if I should remove the comments or if it's going to be... Actually, let's leave them in. So this is the tangent direction x, y, z, and then tangent sign on w. might be useful to say that all of this is local space as well. So this is the data that you get from the mesh. So the mesh data is the input to the vertex shader. So this is where we have all the information that is encoded in all of the vertices, right? And there are only like a limited number of things you can do here. I've already listed like the things I will use 99% of the time. Sometimes I will use like further like UV coordinates from this, but generally the things that I've listed here is like pretty much what you're going to use all the time. I think there are some extra stuff you can get out of this, like especially when it comes to like skinning. I think you can get like bind poses and whatnot, but that gets into stuff that I haven't touched ever. So, all right, so mesh data, here we define what inputs we want to take from the mesh that we care about in this shader. In this case, we wanted the local space vertex position, the local space normal, and the first UV channel, which is UV0. Because most meshes have some form of UV coordinates defined. All right, so this is then, we're gonna skip over this because the mesh data then goes into the vertex shader. And the vertex shader's job is to supply data to the fragment shader and set the clip space position of the vertex. We set the clip space position here, and then we use another structure called Interpolators that is going to be data that we want to pass to the fragment shader. So we set up an interpolator struct, we supply data to this struct, and then we return this struct. And then we're done with the vertex shader. This struct itself, the only thing that you always have to have there is this one. You always need to set the SV underscore position, which is the clip space position of each vertex. Everything else that follows here can be whatever you want. Like you can store data in like maybe this one is an interpolator you use to store, I don't know, some length properties or something. It could be even separate things for XYZW. Like this can be anything, and they're always in the same. They always use the semantics text code 0, 1, 2, 3, and so forth. Not to be confused with these text codes, which explicitly refer to UV coordinates. But in the interpolator structs, they're basically just channels where you want to send data through, right? Okay, so after you set the interpolators, you have now set data for each vertex, and the job of the fragment shader is to render the triangles, right? Because now we're going to render actual pixels to the screen. And all the data you have in each corner of the triangle is going to be blended or interpolated across that triangle. It's not only colors, it's normals, and it's all the data that you pass in there. So if you pass in a value of 1 into an interpolator, and you pass in a value of 2 into the interpolator, the pixel that's going to render here is going to have a value of 1.5, right? Because it's a halfway blend between, because it's a halfway blend between 1 and 2, right? Why do you need text code 0 set in the interpolator if you set the value of the interpolator struct variables in the vertex shader? What do you mean by why you need it? Oh, so I think it's just because it's the way things work. I don't think there's any specific reason. Oh, sorry, this one. Apart from you want to be able to distinguish between which one is the clip space position and which one is just data you want to interpolate, or at least that's how I interpret it. So like this is just a way to enumerate all the data that you want to pass. And the fact that it's called text chord is just a happenstance, right? I wish you didn't have to specify this because it feels kind of superfluous. I wish you could do this and then everything would just work. But that's not how shaders are structured. Yeah, so usually you just, it's just a thing you have to add pretty much. It's annoying boilerplate. Right, so the thing we did in the vertex shader, apart from getting the clip space position, was that we also transformed the local space normal to world space. This was so that we could output this in the fragment shader. Oops. Where did I go? I fumbled my keys too much. So if we output that, that would be i.normal and then whatever value in the alpha channel. So now we're displaying the normal direction. And since it's world space, the orientation of this object is not going to affect the normals that we're seeing here, right? And then the fragment shader itself is relatively straightforward. Fragment shader is usually the one that is the most straightforward because you're not passing anything to anything. You just have data and you want to output a color. That's kind of all you're doing. So before we went for break, we were looking at generating patterns and waves in a shader. So in this case, we were generating this over the UV coordinates, the space, and we just limited it to the X component of the space, right? Yeah, so in this case, we're doing a wave over the X components, but we could do this over like both components as well. We could make this a float too, because all of the built-in functions just work with any number of components. What's going to happen is that for the most part, it's going to do the same operation for every component. So we make this a float too. Then it's going to do this on both axes and visualize it with red and green. So now we have a cosine wave on the x-axis as well as on the y-axis, and we're visualizing them separately using the red channel and the green channel. So like you can juggle these channels very easily back and forth. Anyway, so let's go back to using one. Okay, let's repeat this a few more times. Let's do 5. There we go. So one thing that is very nice in shaders, in the way that shaders work, and that you're kind of just piping math in different directions, is that it's very easy to change the domain in which this is happening. So for instance, we have this value changing by the x coordinate in UV space, right? So the orientation and the position of this object doesn't matter because it's all in UV space. But we could do this in world space if we want to, right? There's nothing stopping us from doing that. And likewise, you can change this to the y coordinate and everything is going to quote unquote just work. The only input we have to this right now is that we have a single value going from 0 to 1, and then the math formula can sort of work its magic, and then it's going to make a wave along that, right? And this has all sorts of implications, but you can very easily get like pretty funky effects with very simple modifications. So for instance, let's say you want to make this wave wiggle, for instance. You want to make this wave, let's see, if we go back here, let's say we want to make this one have a wave where it's distorted in one direction. Well, distortion means that we want to offset it in a specific direction, right? So let's say we make an offset here. So let's call it X offset or something. And then maybe we want to offset this based on where it is vertically, right? That's where we want this offset to be different along. So we can do i.uv.y. We could just leave it at that if we want to. Then we want to offset the coordinate here. So plus X offset, there we go. So if we go back now we have a diagonal wave, because what we're doing is we're adding a value. As we go higher on the Y scale, we add more and more in a specific direction. So now it basically became a diagonal thing. And this looks like some sort of drill now. So if you want to make a drill, you got the shader code right there. But, you know, what if we do stuff like, what if we make this with some trigonometry, right? What if we do the cosine of this? Times tau times 8, for instance. Then multiply that by 0.1 probably. And then go back. Now we have the zigzag pattern, right? We can maybe modify that a little bit further. Make it a little bit less intense. There you go. So now we got this wobbly pattern. Isn't that neat? The thing I really like about this is that it's so like nice to be able to just directly visualize the math that you're doing. And I think it's really neat. And then you can start like making VFX out of this, right? Let's see, what can we do with this? Let's say we want to make this animated, for instance. Then if we want to animate something, we can just very easily access a time variable. So Unity has a built-in time variable called _time. And this one is, again, automatically supplied by Unity. It's a global variable in shaders. And it has XYZW components. It's a little esoteric, but basically the XYZW components use different scales of time. So the Y component happens to be seconds, but the W component is like seconds divided by 20. So if you want to have like different speeds, you can use different components of this, or you can just multiply it. So if we want to change the offset here, we have the X offset here, but then we can add time to this. So if we do underscore time.y, we're now going to add the current time in seconds to this. So now if we go back to Unity and make sure that animated materials is enabled, there we go. That looks very trippy. So let's slow it down a little. There you go. So now you can see that we got this little pattern that's animating over time, right? Isn't that neat? I have to like rotate the camera because for some reason it's like frame rate limited to a really gross frame rate. I don't know, that weird. Anyway, yeah, so these are just like some of the things you can do relatively easily in shaders. And like we talked about before, if you go to like, if you want to make VFX and stuff like that, where maybe you want to have a ring around the ground or something like that. Actually, we can just do that. We can just do that. So let's say we have, oh, maybe we can do that. Actually, I don't know what the UV coordinates are in this thing. So let's say we want to make some sort of VFX thing. First, I'm gonna reverse this so that we're on the other axis. I want to reverse the direction of this. So all we need to do is negate time. Yeah, could hit play, but I don't want to mess up the play state. So if we negate the time, it's gonna start moving in the other direction, right? All right, let's scale this a little bit. All right, so maybe this can be like something that's like a ring around a player, like an effect or something. And then let's say we want to make it like fade out. Because we don't want it to be fully visible at the top. We want it to be a ring along the ground that then fades out the higher we go. So then we need a value that is changing along that axis. And again, the way that you debug things in shaders is that you usually just output some value. So I think the Y coordinate of the UVs, yep, that one goes from 0 to 1. We can use that to then tweak the way that this pattern looks across that space, right? So what we can then do, in this case, one easy way of making this fade out to, say, black, is that we can multiply by it, right? Because if you multiply by a low value, it's going to start getting more and more suppressed toward black. If you multiply by 1, it's not going to change at all. So if we then take this t value, we can then do t multiplied by the y coordinate. So now it's going to fade, right? Although it is fading in the wrong direction, so we might want to reverse this. So we do 1 minus that UV coordinate, and now we have this fading effect from the ground, right? We haven't done anything related to blending yet, so we probably want this to be additive or something. So we could go into that if you want to. I don't really know if we should move on to like lighting, or if you want to like learn about blending already. Is it cheaper to make a thing selected color change with a shader rather than switching materials? It depends, but you can do either. It doesn't really, I don't think it's gonna matter that much. All right, let's do blending in that case. Okay, I'm just gonna ignore the caps of this because I don't really care about the caps. So let's look into blending. Let's say that we want this to actually go into looking more like a VFX type of thing. Then right now, there are a lot of things that are wrong with this, right? We can't see anything behind this. Even if we have something here, it's going to fully obscure whatever object is sitting behind it. So right now, we are rendering this fully opaque. As in, there is no way we can have anything close to something related to transparency in this at all right now. So one of the first things we need to do is think about blending. And blending is a little bit weird in the way that it's set up. Quick little explainer. Okay, so when you have a shader like this, you get a color out of the fragment shader, right? This color that you're getting out of the shader in terms of blending is called a source color. So that's usually shortened as SRC. And then you have the background, as in the destination that you're rendering to. And that is whatever is already behind the object. So that is usually shortened as DST, as in the destination. And the way that blending is set up in shaders, or as in the very cheap version of doing blending that doesn't require extra render targets, there's a term for this, I just forgot what it is. Oh, the back buffer blending. Anyway, so the way that this works is that you have source times some value here. I don't know what to call it. Let's call it A. There we go. Source times A. And then it usually is plus, but it can be minus as well, and it can be reverse minus. So it's source times A plus or minus the destination color times B. So when you define blending, as in you want to change the mathematical formula that determines how this is going to blend with the background, the things you can modify is A right here, and B, and you can modify this operator. So how can we use these alpha colors of the shader to apply textures or colors upon them? We're going to get to textures later. For example, replacing the white with a texture and a black with another. Yeah, we're going to look into textures later, but not right now. Is there time to talk about pre-multiplied alpha? I don't know if I want to go into that. It's so frustrating. Every time I talk about that on Twitter, I always get some extremely frustrating person who has dedicated their life to reading about pre-multiplied alpha, and then they're like taking their time to nitpick about how I used some term incorrectly and like pretends that I don't know what I'm talking about, and it's just really annoying. Anyway, I shouldn't let that affect y'all. I don't know if it's going to matter that much in this case. It might be worth mentioning, but okay. So the way the blending works in shaders is that you need to set A, this operator, and B in order to get the effect that you want, right? That is kind of what you have to work with. So this is the blending. Okay. So with this in mind, you can then do different things. So let's say that you want to do additive blending. So we got additive. Okay, additive blending. Additive blending is the one that I was showing earlier that kind of makes things brighter usually. So if we got, it basically takes the background and you just add to it, straight up add. Mathematically equivalent to just adding. So in this case, you can see that if you have additive blending, it kind of just adds light to it. It doesn't darken anything. In fact, it's completely incapable of darkening, unless you have negative values, I guess. Additive rendering is very useful for like flashy effects, like light effects and whatnot. It's very, very commonly used for like I don't know, fiery things, because you usually get these nice little orange gradients and whatnot out of it that people usually want to have when doing like flame particles and whatnot. So this is additive blending. And I just totally drew that on top of everything else. All right, so additive blending, if we look at this formula, what can we do to make this formula just be source plus destination? Well, all right, we shouldn't be in additive anymore. There we go. So if we want to do that, then all we need to do is set A to 1. So that needs to be set to 1. The operator should be plus, and B should be 1. And that's it. That's how you get additive blending. Because then what's going to happen, it's going to take the source color, which is this shader. Source multiplied by 1 is just the same thing as source, plus the destination multiplied by 1, which is just destination. So that becomes source times destination, or source plus destination. That's how you do additive blending. Very straightforward. Okay, and let's see. Well, what else do we have? We have multiplicative blending. So usually it's called multiply. So if we want to multiply these colors, we want to have source times destination. In this case, what we need to do is we need to set A to destination, and we set B to 0. So what's going to happen then is that it's going to shove in the destination caller here into A. So we get source times destination, and then we do plus destination times 0, which then just removes this factor entirely. So sometimes when you look at blending modes, it's always important to read them in this structure, because when you look at a shader, all you're going to see is this. You're not going to see anything in relation to like additive or multiply or alpha blended. All you're going to see is the words 1 and 1, because plus is usually the default. So if we go back here, then blending modes is defined in the pass, and they're before the actual CG program happens, because it's not in the actual shader code, it's in shader lab, right? So the way you define blending mode is you type blend, and then you enter your A and your B things. And in this case, we want 1 and 1. They're always in words. You cannot enter custom formulas here. There's a very specific set of things you can supply here. But this basically means that it's additive. And then we can add the other one just for completion. We have multiply there. So that one would be DST color would be the destination color, and then 0. So this would be multiplicative or multiply. But we're going to try to do additive in this case. Okay. So let's see what this looks like. It looks like it's sort of additive, but we now have a separate problem. As soon as you start getting into things that are transparent, you run into the issues of the depth buffer, or whether or not you should write to the depth buffer. So if we add a regular Unity sphere, you can see that it sort of kind of works, but it's also got some sorting issues and whatnot, right? So the problem is that this one is currently writing to the depth buffer, and the depth buffer, there's a lot to go into in the depth buffer, but it's kind of just a big screen space texture where some shaders write a depth value, which is between 0 and 1. And when other shaders want to render, they check this depth buffer to see, is this fragment behind or in front of the depth buffer? And if it's behind the depth buffer, it will not render. So basically what's happening is that we have our camera. There we go. And then we're writing to the depth buffer with some object here, right? And what that means is that this is basically going to make the depth buffer go from the far clip of the camera, and then it's going to have values that are really close to the camera because we wrote to the depth buffer here, right? So it's basically going to create this little cone in the depth buffer. And so then if we want to render something behind this object, it's going to skip this. It's going to detect that, well, since we already have something in front of it, we're not going to render this. But whenever you draw something transparent, we can't just write to the depth buffer like this. This method works for opaque objects, things that are not like partially transparent. But as soon as you have something that can still show the destination color, we need to make sure that it doesn't write to the depth buffer. So in this case, we want this one to not write to the depth buffer. So then what's going to happen is that our transparent thing is going to render, and then maybe the opaque thing that's behind it is then going to write to the depth buffer instead. So it's not actually going to affect our additive object right here. Did that make sense? It's a little technical, but you generally don't have to care that much about how the depth buffer works, apart from the fact that it's there to be able to optimize out things that are behind things, right? It's not a draw that is skipped, right? No, the draw will still happen, but the fragments will be discarded very early, even before your fragment shader hits. Yes, so it's a very good optimization in that sense because you skip the fragment shader entirely. But yes, it will not have like anything in relation to like occlusion calling. It's only like a rendering feature. There are many ways that you can like play with the depth buffer, and there are basically two things that you can do with regards to the depth buffer, where you can change the way that it reads from the depth buffer and the way that it writes to the depth buffer. Would that mean that it's kind of heavy to render multiple transparent objects in front of each other at the same time? Yes. The thing about rendering multiple things in a stack with transparent objects is that, let's say you have, let's say this is the camera again, and you have a bunch of planes that all have like some additive texture or whatever because it looks cool. What's going to happen is that it has to render every single one of these. It can't skip any of the fragments. So if you're not careful, you can run into situations where you start lagging. In some games, this is actually noticeable. If you like this is pretty common in particle effects. If you make like large smoke particles, then usually you would have this like large nest of like quads, and all of them have these like large cloud textures on them, right? And so like, especially in older games, sometimes if you walk into like a particle effect with large clouds, your frame rate will just tank completely because these are covering a large portion of your screen, and it means that it needs to do like full screen renders of all of these quads, right? But if you're far away, then if your camera is over here or something, then it's totally fine. It doesn't matter because it's a tiny amount of pixels. But if you get really close, then you have so many layers to render. This is called a fill rate. If you want to have a technical term for this concept. So you want to be careful to not have too high of a fill rate. So what's happening here is that this one is writing to the depth buffer, but we don't want it to. There's also I don't know, maybe it's going to be an issue. We'll see. So that is Z write. Whether or not we want this to write to the depth buffer, and we want this to be off. Let's recompile, and now it seems fine. You might now notice though that we have a separate problem, that this one is being rendered before this sphere, right? So because we want this one to be rendered afterwards, not before. So what's happening is that this one is now writing to the depth buffer and just overwriting everything we're drawing here. So in Unity's built-in render pipeline, basically there's an order in which different types of geometry tends to render. So opaque is, or actually the first thing that renders, it's a skybox. Second thing is opaque, or it's called geometry in the render queue. And then you have transparent, which you usually group like all additive and transparent stuff in. And then after that, you have like overlays, like flares, and like lens flares and stuff tend to go above everything else. Yeah, so that's usually the render order. So when you're dealing with transparent stuff, usually you want to set the render type to transparent. And you also want to set the render queue. So render queue should also be set to transparent. Both of these relate to the draw order, or actually it's mostly render queue that does it. Render type is mostly for tagging purposes for post-process effects. A render queue is the actual order that things are going to be drawn in. All right, let's go back. That did not work. So let's go to Unity, render queue. Not that one. Oh, it's called Q. RIP. There we go. Q transparent. Recompile. There we go. So now we're drawing this additively, and it seems like everything works so far. So if we copy this, you can see that they sort of they all render. They don't obscure each other, and they sort of add together to make this very glowy thing, right? So one thing we might want to do on this is that what if we want this to be double-sided? Because we kind of don't see the other side of this. We just have one side, but the back faces are just gone, right? This is something called backface culling. And backface culling is the default behavior of when you're rendering shaders in Unity. And basically you can tell your shader to either render back faces or front faces or both. So if you say cull back, this is the default value. This means that it has backface culling. Culling usually means that it's a removal of something. You can set that to cull front, and now it's going to flip. So now it's not rendering the front side of the triangles, and it's only rendering the back side. But if you want to render both, you can say cull off. That means it's rendering both sides of the whole thing. So now we even have the front side of it. Okay. Why do you have Q and render type together and both set to transparent? So render type is basically a tag to inform the render pipeline of what type this is. This is usually used for post-processing reasons. This does not actually change the sorting, but it's a useful tag for post-process effects. This one changes the render order. So Unity has a bunch of preset categories. So there's skybox, opaque, transparent, overlay, and so forth. And these are all rendered in that specific order. We want to render all of our transparent objects after everything that's opaque has rendered, because we don't want the depth buffer to write depth values that's going to destroy all of our transparent and additive effects. So we want to make sure that everything that is transparent or additive or multiplicative, all of that we want to render after everything opaque has rendered. So that's why we set the Q to transparent. Okay, so this looks kind of neat. I don't like the fact that we have the upper and the lower part rendering. We can sort of hack that away. Multiplying T by, what's the thing? I.normal.y, or the abs value of that is greater than 0 point something. There we go. No, less than. Now I just hacked away those two surfaces. Basically, I'm using the normal of the surface, and if that vector is pointing either almost entirely up or almost entirely down, I multiply by 0 to just remove those things. It's a little hacky, but you know what? That's how shaders do. Okay, what else do we want to do with this? But yeah, I think this sort of illustrates my point of that you can use all sorts of patterns to create these types of effects, right? Where you want to have some sort of highlight circle around some object. In fact, let's put an object there. There we go. This is now marking the holy sphere. I feel like there was something else I was going to talk about when it came to blending. Oh, there are other things you can do when it comes to the depth buffer. So while this effect shader no longer writes to the depth buffer, but it still reads the depth buffer. Because if we make this one intersect the sphere, you can see that these pixels here are not rendering, right? That is not something that always happens. Sometimes you want to disable that. So on top of zwrite, we also have ZTest for whether or not, or for how the testing should work out when you're presented with a depth buffer with some value, right? The default value is called L equal. It's a little esoteric, but it basically means that if the depth of this object is less than or equal to the depth already written into the depth buffer, show it, right? Otherwise, don't. So L equals the default value. If you want to always draw, you can set it to always. So now, even if this is behind the sphere, it's still going to draw. It doesn't care about the depth buffer whatsoever. You can also reverse it. You can set the ZTest to greater than or equal. In this case, it's only going to draw if it's behind something. And it's not going to draw if it's in front of something. This one is super useful if you're doing stuff like if you have a character effect where you want to show like a ghostly version of a character when they're behind something, then it can be useful to have two shaders that one of them renders when you're behind something, one of them when you're in front. And then so even if you're partially obscured, you can see both versions of it. So you can do all sorts of hackery with the depth buffer. But yeah, in this case, usually you want the default value of less than or equal. Is there n equal to? I don't know if equal and not equal are ever going to be useful because there's only a sliver of infinitesimally small intersections where that would be like where that matters, right? Because that would only mean that where they're exactly the same, it would either show or not show, right? Which only happens at very, very few locations. But there might be. Yeah, if you search for it, you can probably find it. I just never use it myself. Yeah, the ones that are like, there are things you have for like, there is less than equal or less, and the difference between the two can be useful if you want to prevent z-fighting. But other than that, I don't really know what the use would be of an equal or not equal. Okay. Do we still have the colors? We do. Okay. Now that we have this whole thing, we can still use all of this with our colors, right? So let's make a new variable just for readability. Let's call it waves. Float. Top, bottom remover. There we go. That's this one, based on the normals. Okay. Let's say that we now want to bring back our colors. We want to set a color at the top of this and a color at the bottom of this. Let's call this gradient. And we're going to base this off of the UV coordinates y component. So we could just return this gradient to show what it looks like. So this is the gradient. We have color A is at the bottom, and then we have B at the top. So set that to black, fading out, because black doesn't change anything with additive rendering, right? Okay, so maybe, let's see, color A would be the bottom. Let's make that some sort of cyan. And then the top one, some more blue stuff. There we go. Okay, and then what we might want to then do is multiply this by waves. And now we got waves with some colors, right? We have some colors at the bottom. It goes from like cyan to more of a darker bluish tone there. And so like everything you're doing pretty much is just manipulating math and colors and vectors in order to get these types of effects that you want. And again, you can range remap everything if you want to change the contrast of this or the fall off of this. All of this stuff is really, really easy and straightforward to change once you know the math behind it. So you do kind of need to know a lot of math to do this stuff. But once you like harness that, you can make like almost anything. It's wild how much you can do if you know how to write shaders. So I know that it's like empowered me and all the projects I worked on a ton. So it's super, super useful. Okay, let's see. Which thing should we cover during that hour? Emission would be cool. Emission depends on what you mean by emission. In some sense, everything you've been doing is just emission. Because like none of this is affected by lighting. None of this is shaded, as in we have no shadows on anything. So usually when you talk about emissive shaders, this is what you're talking about, as in shaders that are unaffected by shadows, right? But if you want to get stuff that like, if you want a bloom effect or something, like a post-processing thing, that's usually a post-process effect and not something you make like localized on objects in the world. Yeah, so it kind of depends on what you mean by emission. Can we get some wavy effects perhaps? Isn't that exactly what we've been doing? Oh, distortion. That gets easier once you have textures, but we haven't gone through textures yet. Oh yeah, vertex offset. That is something we should definitely talk about. Let's talk about vertex offset. I was going to talk about that earlier and then I forgot. So I'm really glad you brought that up. All right, vertex offset. There we go. I'm gonna paste the existing code, call it vertex offset. Let's create a tessellated plane. What a beautiful plane. If you're working with shaders in Unity, this color, you're gonna see this color a lot. Okay, so I have a plane here. This one is tessellated, so I've like subdivided it into a lot of different triangles, which means that we can deform it because we have a lot of geometry to deform with, right? All right, so let's make a material out of our vertex offset shader. Material, there we go. It is completely invisible. So let's modify this one. Let's first just output the vertex color, or the UV coordinates, sorry. Okay, I don't want this one to be additive, so we're just gonna default all of this. And we're gonna set the render type to opaque, and the default render queue is called geometry instead of opaque for some reason, but kind of annoying thing to have to remember. All right, look at this mango square. Okay, let's bring back our wave along one of the axes. And then remove this one, so we just have the pure wave. Okay, so here's a neat thing you can do. So right now we've mostly been talking about the fragment shader, and we kind of just passed by the vertex shader, which you quite often do. You don't always touch the vertex shader. You kind of just pass data through it. But let's call this a wave. But a really powerful thing you can do in the vertex shader is that you can change the position of the vertices. It can sound a little trivial, like it's not a big deal, but if you consider the number of vertices that we have in this mesh, there's loads of them, right? There's, in fact, 8,192 triangles in this plane. That's quite a lot. So like doing this in like on the CPU of like making a for loop iterating through all of these vertices is going to be expensive, because the CPU is kind of designed to be very specialized and very good at doing like advanced things that are not like massive amounts of data. But the GPU has sort of an entirely different architecture where you have massive amounts of shader processors that can do a lot of work in parallel. And that's exactly what we're doing, right? We have a single shader program. This is the same code that is being run for all of these vertices, right? So now we have this really like parallel processing unit, the GPU, where we can basically do all of this. It's almost free compared to doing it on the CPU, because this is so rudimentary and basic for the GPU to do that it's really, really powerful. And this is also why sometimes the GPU is used for computing or processing data that is unrelated to graphics, just because the GPU is so powerful at processing parallel data and doing that type of math. Anyway, so vertex offset. So now we're gonna add some code that can then change the position of the vertices. So what we can do is we can take this wave and how do you offload processing to the GPU? You write shaders. Instead of doing your code that does whatever it is you're doing, do that on a shader. So like you do that with shader code or compute shaders, and then you can get the data out of it. Usually it's like rendered to some buffer or to some texture, and that's how you get the data back. Okay, so let's take this wave and just straight up copy this one to the vertex shader. So in the vertex shader, we can paste in the wave. Let's see, it's not happy with the UV, and that's because we just have a different word for that. It's called UV0.y. So now this one is reading directly from the mesh data instead of the interpolators, because now we're on a per vertex level, right? This is for each vertex, not for each pixel or fragment. So now we have the same cosine wave here. And then let's use this wave to modify the y coordinate of the vertex. So v.vertex.y equals wave. And in this case, we can actually just leave the negative values in there. So we can just remove the remapping there. So now we have this wave parameter that we're setting the local space vertex y coordinate to. before we transform it to clip space. And then if we go back to Unity, we have this insanity. And this is because the waves are huge right now. We haven't set the amplitude of this. So the amplitude is right now 1 meter. So that's why we're getting this interesting pattern. So we could add a parameter for that. Wave amplitude. Wave amplitude. Probably want that to be like from 0 to 0.2 or something. And then we need a variable for that, so wave amplitude. And then all we need to do is multiply this wave by the amplitude. There we go. All right, so now we got this wavy looking thing. We can set the wave amplitude if we want to make it a little softer. You can also press play to make Unity not run at like 24 FPS. Now we got the very, very rudimentary basic water shader, right? And this is like, again, this is basically free. If you think about the math that we have to do, it's very simple. It's not that much math, right? We're just doing this very simple operation, and we get this whole animation out of it. Do we get purling noise next? Nope. We might do, we're going to do noise with textures, but we're not going to generate purling noise in the shader because that's generally a bad idea because it's very heavy, so it's not very useful in games. It's mostly useful if you're doing shader toy stuff and you want to impress your friends with math. But this is focused on game dev, so. All right, and obviously you can do this, like, you can still keep changing these things if you want, like, if you want to combine multiple waves. Maybe you have a wave 2 that runs on the x-axis instead, and you want this one to also play along with this. Then maybe you have a wave 2 right there. Now you have a multiple wave system that is interacting and whatnot, right? Although the colors are a little misleading right now because the colors are still, we didn't modify the fragment shader, we were just doing this in the vertex shader. How do you ripple? As in like rippling from the center. So if you want to ripple from the center, so you can consider the space that we're doing this in now, right? Actually, we should go back to the fragment shader for this. It's a little bit easier to visualize in the fragment shader. So now we're doing this animation where the domain is the linear x-coordinate of the UVs of this mesh, right? So if we want to make this radial, as in based on the radius or distance from the center, that is the input data we need for this. And right now we're giving it the linear y-coordinate. So what we can then do is that instead of passing this in, we can pass in the distance to the center, right? So if we want to get that value, we can, first we can take the UV coordinates and remap that to a -1 to 1 range in order to center it. So if we just do, if we look at the UV coordinates again, here we go. You can see that we've got 0 here. Oh, this should be based on the x coordinate. We've got 0 here, increasing on the y-axis, increasing on the x-axis, all the way from 0 to 1. But we want to put 0 in the center, right? So then we do the exact remapping thing that we did before, where we remap something from the 0 to 1 range to -1 to 1 range, which is a relatively straightforward transformation to do. You multiply by 2 and subtract 1. And now we've centered these coordinates where 1 is at the edge and -1 is on the other edge. Okay. You can also use inverse lerp for this if you want to be a little bit more descriptive with it, but it kind of depends on how you like want to structure your code and how readable it is to you. But maybe we can make a variable. So float2 UVs centered. Okay, and then if we want to turn this into a radial coordinate, remember that these UV coordinates are vectors, right? They're vectors going from 0 in the center out to some value in this whole space. So what we can then do is we can calculate a distance, a radial distance would be the length of this vector. Is it magnitude? No, length. So then we get the length of this vector, and then we can output that. So go back to Unity. We now have a circular pattern because now every pixel is showing the distance to the center. So far, so good? I hope? Okay, so now that we have this radial distance, instead of using a linear coordinate, we now have a radial one that we can use in the same wave function we had before, right? We got our wave, and instead of using i.uv.x, we can use radial distance here. And then we go back, and now we have this very hypnotizing shader. There you go. And then that's sort of it. And then you can do all sorts of stuff that you might want to do in terms of like, oh, maybe you want to fade it out at some range. If you want to make the ripples not go on forever, then maybe you want to multiply this so that it ramps down as you get closer to the edges. What you can do is then you can multiply wave by radial distance, although this is going to have the opposite effect because the distance is 0 in the center. So now it's going to fade out the center. But what you can then do is you can invert that, right? 1 minus, and then go back. And now we have sort of ripples that fade out the further out you go. Okay, so now we did this in the fragment shader, but obviously we can do this in the vertex shader too. So let's see, maybe we should make a function out of this. Get wave. There we go. Now we get wave. Let's just make sure that this works. Yep. Cool. Okay, so now we can use the same function in the vertex shader. Although, because this is a language like C, and C is absolute garbage, you need to put the function before the place you use it. And I hate it. So you need to make sure that the get wave is above anything you want to, any place you want to use it. All right, so if we want to use that here, then we wanted to do v.vertex.y equals get wave, and then we pass the UV coordinates into that, which is v.uv0. Recompile. Okay, so now this looks like a some sort of Tower of Babylon, or the way that it's usually depicted, I think, or like a birthday cake. Wait, birthday cake? This is a huge cake. So we want to multiply that by the amplitude, right? That we had before. Fountain of wedding cake. Yeah, one of those. There you go. So now you have this goopy three-dimensional wave, the generator thingy. Okay. Although this one only goes above, I feel like the waves should have, they should have negative values. So let's remove this from the get wave. Oh, that's going to get complicated actually if we want to use the same one for the, you know what? It's okay. Whatever. Never mind me. So I think it's better to go through textures, and that would also open up for more possibilities for the assignments I'm going to give you. So let's do textures. Let's see. Let's create a new shader, unlit shader. Let's call it textured. This is just going to be a gallery of very trippy shaders. Let's switch back to another tessellated plane, put it at 0, move away these goops. And let's apply our new material. It's good. It's called textured. There we go. Okay, textures. Let's now jump into textures. Oh, there we go. Okay, first I'm just gonna murder these shitty brackets. LOD we don't care about. Pass we don't care about. Don't care about fog. No fog. No fog. No fog. Go away. Clutters up my shader. Okay, cool. The default state of Unity's unlit shader is that it actually already has a texture. So we can just kind of look at that to see how it works. So you got a property just like any other property, like colors and values and whatnot. But you set it to 2D, and that specifies that this should be a 2D textures. There are 3D textures and there are cube maps, and all of these work in a little bit different ways. But in our case, all we care about is 2D textures. Main text is kind of the default name for Unity's main texture property. Usually that contains the color information on the surface. All right, so pretty standard stuff when it comes to the rest. App data would be the mesh data, and then V2F would be our interpolators. So the thing that is new here is that when we want to sample a texture, you can see that we have the texture here. It's referring to the main text variable, which you need to define in order to be able to sample from a texture. It's called sampler 2D, good to remember. I always forget, and I always have to create a new shader and then check what it says in there. But yeah, sampler 2D, main text. This one is optional. You don't have to define this one. But there, as you might have seen in Unity, textures have this tiling and offset thing where you can set the tiling and an offset for how that texture should be mapped. That's what this is, and this is sort of a magic variable name. If you name it exactly the same name as your sampler and add _st, this is going to be the scale offset. So this one is going to contain all of those values. Unity has a function called transform text, and transform text basically takes those offset values and offsets some input UV coordinates. So all this is doing is that it's scaling and offsetting the UV coordinates so that we can then get those scaled UV coordinates. But this is optional. You can skip this entirely and just do v.uv, in which case it's not going to scale and this thing is not going to matter, right? I almost never use the offset scaling values, so usually I just remove that. But in this case, we might leave it in case we want to tweak that. So what we got here is basically the same thing as before, the same setup with the vertex shader and the fragment shader, but there's a special function here called text2D. Text2D means that we're gonna pick a color from the texture. And the input to this one is what sampler do we want to use when sampling this, or what texture. And the other parameter is where do we want to get some colors from this. So usually UV coordinates are used for like exactly this purpose, for sampling textures. And the space we're working in for textures is from 0 to 1, also sometimes known as normalized coordinates. Okay, so we are getting a color from this texture and then we're returning it, and that's basically it. So if we got this textured one, we can pick a shader. Let's do this grass texture or moss texture. There we go. So now we are sampling from a texture, and you can change the offset and tiling. So tiling would be used for scaling it or stretching it if you want to, and so forth. So that's what the tiling and offsets values are for. But again, they're optional. You don't have to use them. And you can also do this manually the way that we did before, right? Where we directly modify the UVs. So if we do something like o.uv.x plus equals time.y times 0.1. There we go. So if we now go back, you can see that it's now scrolling because we're literally adding to the UV coordinates, which in shaders would mean that it's offset, right? So we now got this scrolling texture. Useful for stuff like if you want to make a river or something. Usually you want to have like panning UVs. There are many different ways you can modify UV coordinates to do stuff like that. You can even use textures to modify the UV coordinates that you're then going to use to sample another texture. It's kind of expensive to do that, but you can use that, for instance, if you want to have, I know Valve used this in Portal 2 and in Left 4 Dead 2, where they were setting up like a texture that would then be able to use as a flow map, as in that one would tell the shader what direction things should scroll in. And then it had all sorts of shader tricks to make sure that you don't get like infinite stretching and whatnot. They were sort of like crossfading between different states as, you know, a texture was flowing in some pattern. But yeah, anyway, so you can do lots of stuff with modifying the UV coordinates. And you can map textures in almost any way you want. You don't have to use UV coordinates. This is a really important thing. And I think it's a shame that like, it's called text coord, which almost feels like it's meant to be used for textures, like UVs are texture coordinates. But I think that is a thing you need to like make sure that you don't like learn, because textures can use any coordinates from any space and across any time, and UV coordinates are not necessarily used for only mapping textures. In fact, most of the work that I've done in the past like 2 years, UV coordinates have nothing to do with textures. I use that for passing data and like other information. So I think it's important to know that like quite often UVs can be used for just passing data that is completely unrelated to textures, and textures don't have to use UV coordinates, even though that is very common, of course. So just to show an example of this, so let's say we want to, you can name these things anything you like though, right? Yes. Well, not the semantics. The semantics have to stay the same. But yes, these are variable names. So let's say we want to, instead of mapping this with UV, in UV space, let's map it in world space. So we have world coordinates. And we want to be able to send the world coordinates from the fragment shader to the vertex shader, or sorry, vertex shader to the fragment shader. So we need this in our interpolators. Okay, so how do we get the world space coordinates? Well, we already have the local space ones, which is v.vertex. So if we do, I usually call it world position, because it's literally the world position of this pixel, right? After interpolation. So what we can then do is we can do a matrix multiplication. So we do mul, which is the matrix multiply function. What we can then do is we pass a matrix in here, which is unity object to world, and then we multiply that by the local space vertex position. You can also use the model matrix if you want to be a little bit more technical. This would be the same thing. All right, so now we're transforming this from local space to world space by multiplying it by the model matrix. And then we can use this in the fragment shader. And as always, if you want to debug stuff, output it as a color. So let's do return i.world position. The world position is a float 3, so we might want to make sure. Actually, it's vertex. I'm not sure if the fourth component of the vertex is 1 here, so I'm just going to make sure that it is. Possibly dumb question. Multiplying by matrix has to be done with mul, or can you just use matrix times vector? I am not sure. I don't think you can do that, but it might be possible. I just always use the mul function. The mul function also has the advantage that you can flip the arguments to transpose the matrix. But yeah, maybe you can do that with just a multiply operator as well. Okay, so I don't know if you remember when we talked about this during our math class, but when you do a matrix multiplication, where you transform some three-dimensional vector, you usually pass a float 4 into that, or a vector 4, where the fourth component, depending on if the fourth component is 0, it's going to transform as a vector or a direction, but if it's 1, it's going to transform it as a position, meaning it's going to take offset into account. If it's 0, offset is not going to be included, it's just going to be the orientation and scale. But in this case, it's a position, right? Okay, so then we want to output the world position, x, y, z. Alpha channel doesn't matter in this shader, so we can just give it whatever value. Okay, there we go. And now we can see, like, would this make sense? We're outputting the world space position, right? Green increases when we move it up. We can see that as we move it around, it gets more red on the x-axis. So it very much looks like we do have the actual world coordinates here, right? So we scale it up. We can see sort of the unit cube in the 0 to 1 range over there. So that seems valid, right? I guess it's especially visible if we put it on a cube. I always love the color gradients you get when you're visualizing world position like this. There we go. We got an RGB cube. So this one is now showing the world position of the current fragment that we're rendering. Cool. So we got world position. Neat. All right. So we got the world coordinates. And world coordinates are in 3D, right? It's along all 3 axes, and we can slice this however we want. Like the rotation doesn't matter. We're just going to get a slice of that unit cube, right? So we know that this value now works. Actually, I'm curious if 1 is the default value here. So I'm just going to try that. Seems like it is. Cool. That makes that formula a little bit easier. So this is object to world. So what did we want to do with this? Right, we wanted to map this texture with world space coordinates instead of using UV coordinates. So if we think about this, what axes do we want to map this texture to? So it looks like it would be on the x-axis and the z-axis, the blue one, right? So it wouldn't be the x-y axis, because then it would be a projection along the z-axis, so that would be a side-on projection. So we want this to be a top-down projection for our 2D texture. So in this case, if we want to get 2D coordinates for our texture, we can call it top-down projection, and then we do i.worldPosition.xz. So now we're going to get a vector 2 out of this that is built from the x component and the z component of the world position. So now we could output this as well. So we can output the top-down projection, which is now a vector 2. And we can see that indeed, we have a 2-dimensional coordinate here. The y position doesn't matter at all, but it is projected top-down, right? So if we rotate it like this, we kind of lose data, and it's not really a planar projection along that axis anymore. Okay, we can then use this as our coordinates for the texture. So we don't actually need to use the UVs. Instead, we can just input our top-down projection, which is our top-down coordinates. And if we then go back to Unity, our texture is now mapped to world space. So if we move this plane, it doesn't matter where we put it or even how big it is. This texture is always going to repeat in world space. So it doesn't really matter how we move this thing around, right? And since it's a top-down projection, edges are going to get all stretched and funky. And if we start rotating this, you can see that we get stretching along the edges, which looks kind of gross. But it works pretty well for relatively flat stuff, right? So this is a very, very common thing to use if you're doing like terrain. So with terrain, you quite often have like vast stretches of land, and then you like blend between different textures. And sometimes it's just kind of easy to just use world space coordinates for that, instead of having to like update some UV coordinates on your mesh every time you change the size of it or whatever. So it can be really useful to have that in your toolbox. Yeah, we do not have time to talk about normal maps. Oh, but there's lots of stuff we can do now that we have textures. Okay, so something that I mentioned before is that like a lot of the things we do, like it's all colors in the end and it's all float force in the end. So we can replace almost anything with anything and it'll just work in the end, right? So just to show an example of this, let's go to good old Photoshop and make a texture. It's gonna be a beautiful texture. We're gonna fill it with just black in the background. All right, let's draw some patterns or of some sort. Cool, what a pattern. Actually, let's do a little bit more of the islandy bits. Perfect. Rate my pattern. Why did I name it pattern PNG? What a weird name. Okay, we dumped that into Unity. Cool. Now let's go back to our shader. We want to have another texture input now. We're just going to call it pattern. There we go. Oh, I didn't really explain what this part is. This is what is going to be assigned if you have nothing assigned to it. So if you want this to be white, if you have no texture assigned, then you type white. I think there's white, there's black, there's gray, and then there's a bump. It's basically a normal map, a flat normal map color. So a normal map that just points directly upwards. Okay, so pattern. Let's bring in our pattern. We don't want scale offset for our pattern. I'm just gonna have the sampler there. And is there such a thing as a single channel texture, or always getting RGBA? There is something such as a single channel texture. Not all of them are supported on all platforms though, and some of them are only available as like render textures rather than like texture data. But yes, they exist. There are like tons of different like shader formats or texture formats you can use. Okay, so I don't really want to use the scale transform stuff anymore. We don't need that. Let's remove it. Let's nuke it. Okay, and then we have our pattern. So what we can do now is that we can let's remove the UV animation. Okay, so we have the color of the grass, right? Or the moss. Let's call it moss just to be a little descriptive. And then maybe we can have another texture now because we have the pattern, right? So let's call it pattern equals, and then we sample that texture just like we did before. But for this one, we can just use UV coordinates, right? So we got our pattern. Let's just make sure that works. Let's assign the pattern, and then also make sure that we use the pattern texture. There we go. So now this is the thing that we just drew in Photoshop, the very beautiful 10 out of 10 pattern. So like I mentioned before, like it doesn't matter if you're sampling a texture, doesn't matter if it's UV coordinates, doesn't matter if you're getting world coordinates. The things we've been doing before, we can do that just as well using a texture sampler as anything else. So when we were looking at this, like we made this wave thing, right? Like the get wave function. Like even stuff like that, we can use the texture for, right? So let's say we change this just to a coordinate because it's not radial anymore. There we go. Okay, so we can do this with the textures as well. So let's say we want to do a wave that's based on this pattern that we just drew. That is completely legitimate and a thing we can totally do. So let's try that. Let's do get wave from this pattern. And then we have an undeclared identifier. An undeclared identifiers happen when you don't have tau in your shader. There we go. So now this thing is based on the texture instead of being based on some math, right? It's a little bit compressed. It looks a little garbage if you zoom in. You can of course change a bunch of compression settings. You can set the compression to none, in which case it turns off compression. But if you turn off compression, then obviously that's going to take more memory in your. It's going to occupy more memory in your GPU. Might also want to do that so that it's not flashing all the time. But yeah, so like I mentioned, you can just like keep doing this like over and over and over again of like swapping out values and spaces and coordinates to achieve all of these like funky effects that you might want to achieve. Anyway, that was just an example for how you can like swap these values out. Okay, otherwise we now have this pattern. I should specify that that's the X component. Right. So now we can do stuff like, what if we want to have grass wherever this thing is white, for instance? Well, we can use a lerp for that, right? So let's say float for final color equals lerp. In this case, I guess we can just have a constant of, let's make it red. Let's blend between red and grass, right? Or moss, based on the pattern that we just had. And that's a float for. And then we return that color. So now if we go back, we're now blending between the color red and our grass texture. And these are sampled in different spaces, right? Because one of them is sampled in UV space. So if I scale this, the pattern will also scale, but the grass will not scale. So we can sort of move this around, and they're kind of moving independently of each other, which is kind of neat, right? So you can mix up these spaces as well. Not everything has to use the same space. And then obviously you can also blend between different textures. So let's add another texture. Let's call that rock. All right, copy the variable. And then we have the moss here, and then we can replace this with a rock. There we go. Use the same top-down projection for that. And blend between rock and moss. Okay, let's go back to Unity. It's white because white's the default and we haven't assigned this yet. So let's replace that with the rock. And there you go. So now we're blending between these two textures. And they're also both in world space here, right? So this pattern is only changing where they are blending, but it's not actually changing the mapping of these textures, right? Because the textures themselves are sampled in world space. And obviously this blend looks kind of horrible. It's very, very, very like obvious that it's crossfading between two textures. So quite often you would use other like noise textures to modulate this blend. But I don't know, we probably don't have that much time to look into that now. And I also need some time to create some exercises for y'all. Okay, I'm gonna make a Unity package out of all of these things, and I'm gonna send it to you so you have the code in case you want the code. If you're watching this on YouTube in the future, it's gonna be below in the description. I'm gonna link the things. Same thing with the assignments. I'm also gonna link that in the description. But we're still stuck in the past, so there's no description here. My students are saying the future people should like, comment, and subscribe, and hit the bell for notifications. There you go. Any more questions before we're done? So we did textures. That's really good. Lots of fun assignments we can do. Oh, one final thing that I should talk about, which is a very neat topic, which some people might not expect to be a thing that shaders have. Here's a fun fact. Actually, let's use this texture as an example. It's probably a good one. Okay, so when you think about a texture, this obviously needs to be loaded into memory of your GPU, right? It has to load this whole texture so that it's ready to read from it as soon as you want to draw something with it. There is something that is really useful to know about when it comes to textures, is that this is actually not what lives in your memory. It's not just what you're seeing in front of you right now. You can make it so that it is that, but that is actually pretty bad. And this relates to something called MIP maps, or MIP maps, usually just MIP maps. And what MIP maps are is that you have basically copies of this texture, but downsampled to different sizes. So the way that this is going to look in your memory, in most cases, is that it's actually going to take twice the amount of memory. Worst case, 4 times. Quite often, your textures are not properly copied in Photoshop. Oh god, I turned off snapping. View, snap. There we go. So what often happens is that your actual texture in your video memory is going to have a downsized version of itself quite a bunch of times. And usually it's a halved in size for every scale along the way. So it's something like this. I'm not perfectly aligning these, so this couldn't actually be used in a real world scenario, but you get the idea, right? All the way down to a very, very, very low resolution. And this one is just a bunch of pixels. So what we end up with is a texture that sometimes takes like twice the actual amount of memory because it has to fill these extra MIP spaces in here. And you might wonder, like, what is the point of having MIP maps? Like, why do we even do this, right? It just takes up a bunch of extra memory. And the fact that you do that is, or the reason you do that is because if you think about how shaders work, if some texture is far away, you have some UV coordinate on some pixel, it's actually just going to take the color of that pixel and output it in a very naive way if you don't have something like this. So we can actually look at what would that look like if we turn off MIPs. So I'm just going to make both of these moss. This might be difficult to see on stream. Is that actually how they are packed? It depends on a lot of factors. If you have I think some of them do one on the side and then it's sort of up in a sort of spiral-like manner. I think some of them do, oh god, what's the order of these? I think you can do this type of thing, which is a little bit more space efficient and whatever. But if you have anisotropic MIPs, it's not going to look like this at all, because then you need anisotropic data and not just isotropic data. So it's a simplification of it. Okay, so if we want to turn off MIPing, we can very well do that. So if we go to our MOS, we can set anisotropic level to 0. We can uncheck generate MIP maps. And now it might be difficult to tell, but there should be a lot of noise happening now, right? Anisotropic is for anisotropic filtering, right? Yes. So you might be able to tell that this is kind of flickering and it's very noisy, right? And this is because now we don't have the MIP information. We don't have this pre-downsampled versions of this texture. We could do the same for the pattern, I guess. It might be more obvious with this pattern since there's more contrast in it. So if we turn off the MIPs, although this one is more soft. No, never mind, bad example, it's too soft. But yeah, so there's lots of noise here. Okay, so it's actually not, so the reason for having these MIP maps is that they are downsampled so that when the texture, or when the shader is going to sample from this texture, it can sort of guess at how far away the texture is. And it's actually using partial derivatives to figure this out. And based on the rate of change of the UVs that you're sampling with, depending on that, it can pick a lower MIP that matches the distance at which you're sampling this in. And then there's all sorts of stuff you can add on top of this. The very basic types of MIPs that I show you here, that one is purely distance-based. It doesn't really care about angle. It does to some extent, but it's isotropic. You can enable anisotropic MIPS, which that one stores squished versions of these as well, that are like squished on some axis. So not only do you have the isotropic ones, but you also have anisotropic versions that are scaled on a specific axis, right? Which is useful for when you're viewing something at a very low angle. So if you have ever heard of like anisotropic filtering, that is what anisotropic filtering is. It stores some number of MIPS like this that are squished along a specific axis. So they're like pre-filtered and look really good at like low angles, which is really, really useful for like games where you have like a camera that's close to the ground, like FPS games or whatever. Not as useful for like RTS games. Anyways, that's anisotropic filtering. So if we enable MIP maps again, but we don't have anisotropic filtering, then if we view it at a grazing angle, you might be able to tell that it's kind of blurry here. Because now it's picking from one of the lower MIP levels, or higher? I don't know which way it goes. So now it looks pretty blurry on the horizontal axis, right? But if you enable the anisotropic MIPS, the blur disappears immediately, because now we have pre-sampled versions of, you know, what would an ideal squished version of this look like along, you know, both the cardinal directions, right? Yeah. Games tend to say that it will induce a performance hit, but I rarely noticed any from that. Is it mainly just a memory issue? I think it's mainly a memory issue. But yes, most games say that it affects performance, so I would guess that it actually does. But yeah, anisotropic filtering generally does take more memory. But it could be something like the partial derivative needs to like separate out the different axes in order to like calculate that, and that might be slightly more expensive. But yeah, I've never had issues with like performance when it comes to that. So, oh, and then there's a third concept which is also really useful. So you can have different filter modes. Bilinear is the usual filter mode, and you can also have point filtering. So point filtering is what kind of gives you the Minecraft look, where it doesn't blend between the colors between each individual pixel. It just goes to the nearest neighbor, right? So that's when you have a completely unfiltered texture sampling. Bilinear means that it's going to blend between these textures. Bilinear is pretty much always default at this point, and point sampling has a lot of anti-aliasing issues unless you make a very specialized shader for it. And then you have trilinear. Trilinear means that not only does it blend between the pixels smoothly, but trilinear means that it also blends between the different MIP levels. So it used to be that if you don't have trilinear filtering enabled, you could quite often see like wandering ridges if you move along the surface. I can see it on my screen. Like there's one ridge here where it's switching between the different MIP levels. Probably not visible on stream. But if you enable trilinear filtering, it's going to blend between the different MIP levels, in which case we're not going to have this blurriness issue. Again, mostly useful for like FPS games where we have a lot of low angles looking at terrain like this, in which case it's really good to enable all of these things. But for RTS games, it's pretty much is a waste of memory. Okay, cool, we did it. We talked about textures. Right. How is the filtering applied as kind of post effect? This is very low level GPU stuff. It's not a post effect. This happens when you sample the texture. I don't know exactly where it happens in the GPU, but if you want, you can explicitly sample a texture at a specific MIP level if you want to. In some cases, you actually have to do that. But if we do, for instance, let's just return the moss. Let's add a MIP sample level. MIP. That's a integer. Oh, sometimes you can sample float. I have like weird behaviors between platforms. With this, 0 is the highest level of detail, and higher numbers step down into the lower levels of detail. All right, so we got the MIP sample level. Let's call it a float. So if you want to sample a specific MIP level, you can use text2d LOD. for level of detail. And then the UV coordinates are going to be a float 4, where the MIP level lives in the remaining parameter. I think that's how it works. I don't know if I need both of them. I think you have a float 2 here if you want to do like separate for the X and Y coordinate or the U and V coordinate. And that's for anisotropic sampling, but in this case, we just have a single value. So now if we go back, we can change the MIP level right here, right? So if we set it to 0, we have the highest level of detail, and we're going to get this issue again where if we're far away, it's going to look all noisy. But if we can change the MIP level here, and if we're really close, it's going to look blurry. But if we're far away enough, it's going to look just fine, right? But yeah, so this is something you can use. MIP levels are sometimes exploited for like specific effects. They're quite often used in lighting, like image-based lighting. Sometimes you store like convoluted as in the lighting scientific term, convolution of light, in like a cube map, for instance, in which case the MIP level can sometimes be sampled depending on like if you want to have a blurry reflection versus a sharp reflection. You can read off of textures at different MIP levels. So sometimes you do want to get a specific MIP level for like technical reasons or artistic reasons and so forth. Usually you just let the GPU calculate the MIP level automatically in most cases. Another caveat is that if you sample textures in the vertex shader cannot figure out MIP level automatically. So you can't use the text2d function inside of the vertex shader, but you can use the text2d LOD function in the vertex shader. So just a little thing to keep in mind, that if you ever want to use textures in the vertex shader, always use text2d LOD because it needs a specific MIP level supplied to it. Okay, that was a lot. Sorry for like rushing MIPs and textures, but I wanted to go through textures before we end for today. Okay, I don't know when I'm gonna have the exercises ready. Any questions before we're done for today? If a texture is rendered at a big distance, only small MIP is used. Is a whole texture atlas still loaded into memory? That depends on how you set up your like texture pipeline. There are like some games that can like dynamically stream in and out different MIP levels, which is why sometimes games prioritize lower MIP levels and then load the higher detail ones later. Like I know Unreal Engine 3, I think, had a pretty aggressive feature like this, where they prioritize load times really, really heavily. So you would sometimes like spawn in like some area and you would see everything would just be a smeary blur, and then it would like get more and more detailed as time goes on. So sometimes game engines do that, yeah. This is very informative. Looking forward to the assignments in the next lecture. Thanks. For the sake of efficiency, can you prepare the assignments ahead of time, like before the course starts or something? Also more likely to guarantee the quality of them as well. I don't like doing that because I don't know how far we're gonna get in the course. I feel like if I force specific things that we're going to cover, I'm going to either rush some of them or I'm going to have to like draw some of them out in order to not cover things that I want to cover in the next one. So I tend to prefer to do this on the fly, because then I know exactly what I've taught to you and what I haven't taught yet, to make sure that like the assignments only cover things you already know. But I mean, if you don't like the assignments, feel free to tell me if they're not good. But I try to make them good regardless, even though I do all of this basically improvised. So can you get these scripts as well? Yes. I will send you all the things. Okay. Also, thanks, Oliver. Could you swap out the stone texture with a water one and make the waves again? I don't have a water texture, Digga, so not really. Okay, cool. I guess we don't have any more questions. Feel free to play around with shaders until you get the assignments. But yeah, otherwise, just experiment. There's a lot of like fun to be had in just experimenting with shaders. And I will send you all the code from today as well, so don't worry about that, including the textures. I should also fix all of the MIP settings that I destroyed. Oh, actually, if you want these assignments as well, I guess feel free to head over to my Discord, and I'll post them in the dev channel. Probably I'll post them somewhere, in case you want this package as well. For those of you on Twitch. But yeah, Thor is screaming. I should wrap up this stream. I hope this was informative or interesting or fun or whatever. Also, huge thank you to Future Games for like even allowing me to share this publicly. It really helps incentivize it for me because I want to be able to reach a lot of people. And it's kind of a shame to me if I do like a whole thing and it only reaches like 20 people. I think it's really nice that like even people who aren't part of Future Games get to take part in this. So I'm really, really grateful for Future Games to for allowing me to do this. It's really nice of them. Yeah, I think that's it. Thank you all so much for joining.